PU2 aspirants, so chemistry PU2 final board exams is very near, and today in this video we are going to revise the complete organic chemistry. So we are going to do all the revisions of the reactions, and I'll be also solving some 20 questions per chapter. So there are 5 chapters, almost 20 questions I'll be doing. So 100 plus questions we will be practicing today, and these questions have been taken from your NCERT in-text questions, previous year questions, and also from your PU2 question bank. Okay, so all the important questions I have collected, so let's dive in. And I want all of you to sit with a notebook and pen and note down all the reactions. I have just flow charts of the reactions, so you have to draw this flow chart so that you can revise it quickly. Okay, so now in today's class we are going to cover these chapters. Okay, haloalkanes and haloarenes, alcohols, phenols and ethers, aldehydes, ketones and carboxylic acids, amines and biomolecules. Okay, now here what all things will be what all things will be doing here. So we will be doing all the reactions revision. Okay, so reactions whatever are there in this one chapter, we will be revising it properly. Then we will be solving all in-text questions and previous year questions as well. Okay, but I will be coming with a separate video of 5 marker questions. So basically in this I will be dealing with 2 and 3 marker questions. Okay, but it's not that only 2 and 3 marker, but major focus is on 2 and 3 marker. 5 marker questions, a dedicated video will be there, so do not worry. Okay, fine. Now moving to the first thing, how can you expect, what can you expect from this? So full marks in your section D. So as I told you, 5 marker section. See, here's a small thing. You might think that ma'am, you told that you won't give more importance to 5 marker question, then how are we going to get full marks? So see, the 5 marker section generally is like 3 plus 2. Okay, so I'll be giving you 3 marker questions and 2 marker questions so that you can solve these all the questions and get full marks in your section D, that is 20 out of 20. Okay, fine. Now moving to the first chapter, haloalkanes and haloarenes. So I told you basically we are going to revise the reactions and question solving. So what all reactions we have to study? Preparation of haloalkanes, preparation of haloarenes, chemical reactions of haloalkanes and chemical reactions of haloarenes. Okay, fine. Coming to the first thing, that is preparation of haloalkanes. So I want all of you to draw this, whatever I'll be showing now. This is very, very important, and you should do in this way only to revise these things. Okay, so basically, okay, so preparation of haloalkanes, we have 3 medium, or there are, so you should read always horizontally. Okay, then you should have a clear idea horizontally, then go for vertically. So if I say preparation of haloalkanes, I have 3 methods. First is from alcohols, second one is from hydrocarbons. Under hydrocarbons we have again 2 methods. One is alkanes, another is alkenes. Then we have halogen exchange method. Under that we have 2 reactions, that is your Schwartz reaction and Finkelstein reaction. This picture should be clear in your mind. Okay, whenever I talk about preparation of haloalkanes, immediately this diagram should flash in your mind. Getting from alcohols, from hydrocarbons, under that we have alkenes and alkanes, then halogen exchange reaction, under that we have Schwartz reaction and Finkelstein reaction. Okay, now coming to under alkenes, we have again 2 things. One is addition of HX and addition of X2. Okay, so these all things I will discuss, but I want all of you to draw this. Okay, take one A4 size paper. On the first half of the A4 size paper, please draw this one. Okay, like you have to divide your A4 size like this. Okay, on you can either divide like this and make this scheme, this one here. Okay, and give here haloalkanes preparation, give the heading, draw the scheme here, and here we will do the flow chart of the reactions. Okay, so this part is there, and this side is preparation of haloarenes. Write down here, make it, then I'll be telling you what you have to do here. Okay, I hope this is clear. This is how you have to prepare a short note right now so that you can revise it 100 times before the exam. Okay, just 100 times means many times you can revise before your exam. So first one is coming from alcohols. Okay, so alcohols, what we have to do? You can take any 6 of this, any one of these 6 reagents to get alcohols, to get haloalkanes from alcohols. For example, you can treat it with HCl and ZnCl2, you will get RCl. You can treat it with NaBr and H2SO4, you will get RBr. You can use PX3 to get RX. Here in PX3 and PCl5, please remember the byproducts. Questions can be asked from byproducts as well. So how will you remember? In PX3, you see this is a small compound. PX3, only 3X is there, right? So that means just I'll tell you how I am remembering. So PX3 is a small compound, so there will be less number of products. So one is definitely RX, another is H3PO3. Okay, now PCl5 is a bigger compound, so there will be more products. So one is definitely RCl, then we have POCl3 and HCl. Okay, so these two, please remember the byproduct. Next I have X2 and red phosphorus. Here X2 can be bromine or iodine. You will get RX as the major product. Then SOCl2, you will get RCl plus SO2 plus HCl. Okay, now here you should remember that this SOCl2 is called as thionyl chloride. Okay, this is the first thing that we should be knowing. Next, what else things we should be knowing? That this is the most preferred method. Okay, the question can be asked that the reaction with SOCl2 is most preferred method. Why? So you have to write down this reaction, and the reason that why it is the most preferred method is the byproducts are produced in gaseous form. So what will happen? This SO2 is a gas, HCl is a gas, right? So they will evaporate. So in the container you will be having only RCl group. Okay, so from alcohols, what all reagents we have? Can we just revise them? So from alcohols I have 6 reagents, right? The first one which I remember is the most preferred one, HOCl2. Then I have Zn and HCl. Then I have PCl3. I have PCl5. Then I have X2 and red phosphorus, and then I have NaBr and H2SO4. Okay, clear? Next we will go to the next part, that is from hydrocarbons. So from hydrocarbons I told you we have two things, from alkanes and from alkenes. So from alkanes the free radical mechanism is there. Okay, free radical halogenation is there. So CH3, CH2, CH2, CH3, if you treat it with chlorine H nu, all the hydrogens can be replaced. So you can get one product here where this hydrogen is replaced, and here you can get one product where this hydrogen is replaced. Means the different types of hydrogen can be replaced. So this here a question can be asked, that is not a preferred method. This is not a preferred method. Why? This is not a preferred method. Why? Because we get multiple products. Okay, we cannot get only this one or only this one. We will get a mixture of products, or you can better write mixture of products instead of multiple products. Just write down mixture of products. So it is not a good method. Next, if I see from addition of from alkenes, okay, so from alkenes is addition of HX. You have this one, if you add HX, Markovnikov's rule will be followed. According to Markovnikov's rule, what happens? The negative part will go to the carbon having less number of hydrogen. So here I have one hydrogen, here I have two hydrogen. The X will go to the carbon having less number of hydrogen, so that is this one. Okay, now coming to Markovnikov's rule. You can write down what is Markovnikov's rule, but here we have one exception, that is anti-Markovnikov's rule. So if I use HBr in presence of peroxide H2O2, so what will happen? Anti-Markovnikov's rule will be followed, and the negative part will go to the carbon having more number of hydrogen. So I will get this as the product. Okay, now coming to addition of X2. Addition of X2 is very simple. We have to use X2 in presence of CCl4. The double bond will break and X will be added. So this type of this type of what I'll say haloalkanes, where the two adjacent carbons are having the halogen. You can see these are two adjacent carbon, they are having halogens. These type of halogen are called as vicinal dihalides. Okay, vicinal dihalides, or this is also called as alkylidin dihalides, alkylidin halides. Okay, here I want to introduce you to one more term. If here you can see two nearby carbons are having X. Okay, now if the same carbon is having X, then we call it geminal dihalides. Okay, and what is the common name here? Alkylin dihalides. Okay, this can be asked in the MCQ question, so do not worry, I will cover the whole concept, everything will be covered when it is required. Okay, so just follow with me, write down whatever I am discussing. Clear? Next, moving to the halogen exchange method, the third method, halogen exchange method, we have two important reaction, Finkelstein and Schwarz reaction. These two reactions are very important, you have to memorize it. Okay, so in Schwarz reaction what happens, we take any, so generally here X is chlorine or bromine. Okay, you take any haloalkane, or I can say chloroalkane or bromoalkane, then treat it with metallic fluorides to get fluoroalkane plus the metallic chloride, metallic halides. Okay, so this is your Schwarz reaction, and Finkelstein reaction is for the production of Ri. Okay, so here you take any haloalkane or especially chlorine and bromine, treat it with NaI and dry acetone, you will get Ri plus NaX. Okay, so this is the reaction, two important reactions. Okay, so with this we have completed the preparation of haloalkanes. Let us quickly revise it. Okay, one short revision for the preparation of haloalkanes. So basically, if I want to draw a flow chart of the entire thing, so please do with me that below space I left, right? If you see, this was the paper I told you, take a A4 size, here you have to draw that scheme, and here you have to draw, which I am doing right now. Okay, so just a minute. Yes, so please do it with me. I cannot show you again because this is not a new slide, it is added here, so it will be erased when I go to the other slide. So please do it with me. Preparation of haloalkanes. Okay, first I have from alcohols. I'll write number 1, from alcohols. Okay, then I will write here any ROH. Okay, next I know there are 6 methods here, so I will make 6 lines like this. You will be knowing that it is going here only, so no need to worry. So first one is HCl and ZnCl2. Second one is NaBr and H2SO4. The third one is PX3 PCl5. Then you have X2 and red phosphorus, right? Last one, do you remember? Very important one, SOCl2. The most, what I'll say, the most preferable method. First one is done. Second one is what? Second one I will write from hydrocarbons. Okay, and from hydrocarbons I have 2 things. One is alkanes, so I will just write down like this, Rx. Okay, then here what is the reagent used? Cl2 and HNu, and I have, so I am writing here alkanes. Okay, next here it will be alkenes. So I have like this alkenes, then I have to use what? You have 2 methods, one is Markovnikov's rule and anti-Markovnikov's rule. If you use HX, then this is Markovnikov's rule. If you use HBr in presence of H2O2, then it is anti-Markovnikov's rule. See, in the short notes it should be very crisp, you don't have to write much, but you have to write all that is important. This is done. The third method what we have is halogen exchange method. Halogen exchange method, right? Now here also I have 2 reactions, so I will write like this. One is I'll put just a minute, I will write like this. This side I want to write, right? So it is like okay, I'll write like this. One is your Rx plus NaI, okay, and here I'll get dry acetone, right? So this is my Finkelstein reaction, okay. The another one is Rx plus AgF, or any other metallic fluorides you can write down, or any other metallic fluorides will give you this one, and this is called as your Schwarz reaction, okay. So this should be there, a complete picture of all the preparation methods of haloalkanes and okay, only haloalkyls. All the preparation method is done in one single section of a page, okay. This is what you have to draw, or you can take half page if possible. If you are not able to do it, try to fit in 1/4 of the page, but if not, you can extend it, okay. Now we will, I hope this is there. Please take a screenshot of this. This will vanish because I am going to change the next slide, okay. Clear? Now we will go to preparation of haloarenes. So here we just have two methods, so nothing much to remember here. The first one is from hydrocarbons and second one is from the amines, okay. So under amines again we have two things, two reactions are there. One is your Sandmeyer reaction, okay, another is your Gattermann reaction, okay. So from hydrocarbons, how can we prepare haloarenes? So you can see, if you have this one toluene, right, this is toluene. If you take toluene and react with X2 in dark, so please understand, there is a very important question. If you have any like this CH3, CH2, CH3 and you are treating it with chlorine in UV light, okay, then this part will, okay, not like this. I will show you the difference like this, just a minute. Very important difference, please see. If you have CH3, okay, and if you treat chlorine in presence of UV light, so what will happen? This part will get chlorinated and you will get CH2Cl, okay. But if you take here chlorine with Fe dark, then what will happen? This part will not react, the benzene ring will react and you will get chlorine in the ortho position and in the para position, both will be there, okay. So you see the difference here. If dark is there, ring will be affected. If light is there, the aliphatic chain will be affected, okay. Next, reaction with I2 are reversible in nature. So if I just do reaction with I2, here what happened? The reaction will reverse. So that is why the fluoro, okay, so that is why we cannot prepare iodobenzene with this method, or fluoro compounds are not prepared due to the higher reactivity of fluorine. So two questions can be asked here. Why cannot be fluoroarenes be prepared by this method? Because of their higher reactivity. And what's the problem with iodobenzene? That is I2 produced here. I2 here. The reaction with I2 is reversible in nature. Okay, so that is why we cannot do this reaction. So two questions can be answered from here. Next we'll go to Sandmeyer reaction. So that is actually from amines, I told you. So we have two here, Sandmeyer and Gattermann, but I have written only Sandmeyer. I'll show you the Gattermann also. So first of all you have to take aniline, okay, react with NaNO2 plus HX. This whole thing can also be written as HNO2. Do not get confused if it is given as HNO2. This is called as nitrous acid, okay. Now what will happen? This NH2 will get converted to N2 plus and Cl X minus, whatever you have taken X, generally it is chlorine. Now this particular compound is called as benzene diazonium chloride, okay. So from here if you treat it with Cu2X2, okay, then this is called as Sandmeyer reaction. You will get chlorobenzene or bromobenzene, where X is chloro or bromo. For treating it with or to getting iodobenzene, you can treat it with Ki, okay. Now apart from this, I told you there is one more reaction, that is your Gattermann reaction. So if you treat it with Cu and HBr or Cu and HCl, then you will get this one, that is chlorobenzene or bromobenzene. Clear? This is what? This is which reaction? This is Gattermann reaction. Done? So we have only two methods. One was is your chlorine in dark, another is from amines, that is Sandmeyer and Gattermann reaction. With this, the preparation of haloarenes is over. Okay. So students, we have now discussed the preparation of haloalkanes and haloarenes. Now we will talk about the chemical reactions of haloalkanes. Okay. So if you see here, chemical reactions of haloalkanes, there are three types of reactions. First is nucleophilic reactions, then you have elimination reactions, and then we have reactions with metals. Okay. Under reactions with metals, we have Grignard reagent and Woods reaction. Okay, and under nucleophilic reactions, what we will be studying, different types of nucleophiles that can react with your haloalkanes, and next one is your type of reactions, types of nucleophilic reactions. This is very, very important. Okay, this is very important concept. From here questions are being asked, so we will discuss about it. So let us see quickly. Basically, I will explain you first how does a nucleophilic substitution reaction looks like. See, Rx is there, and this nucleophile will be there, and nucleophile we all know it is an electron rich species, right? Now this nucleophile will replace this X and we will get R nucleophile plus X minus. Okay, so this is basically your nucleophilic substitution reaction. Okay, now what happens, we will see what all are different nucleophiles that are available. For example, if I use KCN, okay, then what is the nucleophile here? Cn minus. So if I use KCN, I will get RCN. If I use AgCN, here the nucleophile is NC, that is isocyanide, and here I will get RNC. So like this, I have a table of all the nucleophiles. You can see here. If I want to add OH minus, I want to replace the X with OH group, then you have OH minus. For that you can add NaOH or KOH. Similarly, if you add water, then also you will get ROH. If you get NaOR, here RO minus will be attached and we will get ROR, which is a ether. To change to I, you have Rx and you want to make it Ri, and that is your Finkelstein reaction. You can use NaI and you will get alkyl iodide. If you react with NH3, Rx and NH3, you will get amines, that is RNH2. Now if you have this RNH2, okay, R dash NH2, and you are reacting it with this one, again this one is reacted with this one, so here it is like this. If you have RNH2 and you are replacing, I am writing it like this, R dash X, then what I will get, this H and X will form bond and we will have R dash N, H and R. Okay, so like this reaction we have studied, we will study in detail in amines, so we can leave it for now. Then if you want Cn minus KCN, AgCN, if you want NC, isocyanide, KNO2 will give you ONO, that is your alkyl nitrite, and AgNO2 will give you NO2, and that is nitroalkanes. Next you have RCOO minus Ag plus, so we have RCOO minus and that is RCOOR. Ester, LiLH4H, we will get RH. So if you just treat it with LiALH4, what will happen? This X will be replaced with hydrogen and we will get a hydrocarbon. Similarly, if you take react with any Grignard reagent R-M plus, R- will be the nucleophile, you will get RR, and that is an alkane. Okay, so these are the different types of nucleophiles, so you should be remembering these nucleophiles. Now coming to types of reactions. So basically there are two types of reactions. The nucleophilic substitution is, one is your SN1 mechanism and the other is SN2 mechanism. I hope all of you would be knowing about this. So in SN1 mechanism, what happens? The Rx will first give you R plus and X minus. Okay, this bond will go. This is step 1 called as formation of carbocation. Okay, now the second step, what will happen? Second step is attack of nucleophile. So you have here R plus and here you have nucleophile. The nucleophile can attack on this one and you will get RNU. Clear? So this is your SN1 reaction. You can see we are getting Rx to Nu, but there is in between there is an intermediate form which is called as carbocation. Okay. Now in case of SN2, what happens? In case of SN2, you have Rx and here we have the nucleophile. The nucleophile attacks from the opposite side, and we get a transition state like this. Nucleophile is there, R is there, X is there. This is a transition state is there, where this bond is forming and this bond is breaking. So I will get NUR. Okay. So here what we are observing, the nucleophile always will attack from the back side. Okay, it cannot attack from the front side because X is there, hindrance there. Okay, here what happens, a carbocation is formed, there is no X, so nucleophile can attack from front side also, back side also. We will get two enantiomers product here. So this product we will get here, it will be of two, like where suppose one from the front side and one from the back side. So we will get a racemic mixture here. Okay, but here we will always get the inverted product. Okay, now I'll give you the difference between SN1 and SN2. It will all be clear. It is a unimolecular reaction, means only one. When you see in SN1, in the first step there is only Rx. Okay, there is no nucleophile there. It is a unimolecular, it is a bimolecular, because in the first step we have both R, Nu and X. Similar, you can see the follow other points. It follows first order kinetics, second order kinetics, two step, one step. Okay, it depends only on the concentration of the substrate, depends on both substrate and nucleophile. Here there is carbocation formed, no carbocation formed. There is no partial bond formation. Here is partial bond formation. The nucleophile attacks from the both the sides, although backside attack dominates. Here it always only attacks only from the backside. Here partially racemized product is formed. Here only inverted product will be formed. Mild nucleophile, and here we have strong nucleophile. It is favored by solvents of high polarity, and here we have solvents of low polarity. Now rearrangement of products takes place, and there is no rearrangement. Why? Because here carbocation formation is there. And 12th one, the order of the reaction for SN1 is 3 degree, 2 degree and 1 degree, and for SN2 it is 1 degree, 2 degree and 3 degree. Okay, so these differences you can remember, any three differences can be asked, so please prepare any three differences and both the mechanisms. Okay, now we'll go to the second reaction, that is elimination reaction. So for elimination reaction, the reagent that we need is alcoholic KOH. Please remember this one. So what will this alcoholic KOH do? So this is your X, this is alpha carbon, this is beta carbon. So this alcoholic KOH has the base OH minus, right? So sorry, the base here, whatever it is, RO minus actually, okay, because we have alcoholic KOH and gives you RO minus. So this base attacks H plus, it takes the H plus, here the double bond is shifted and this goes out and we get a alkene product here. But here the thing that you should be remembering something is your Saidzev rule. Okay, according to Saidzev rule, what happens? Most substituted alkene is formed. More substituted alkane is formed. So now here if you see CH3, CH2, CH2, Br and H. So this is also alpha carbon, this is also alpha carbon, so this is also alpha hydrogen, this is also alpha hydrogen. So HBr can eliminate from here, we will get a product here. HBr can eliminate from here, we will get a product here, right? Double bond is here and here the double bond is here. Now which is more substituted? To check that, you have to see that around the double bond there should be more number of carbons. So here you see there is 2 carbon, right, this carbon and this carbon, but here if you see there is only 1 carbon. So more carbon is there, more substituted, so this is formed in 81%, that is formed in 19%. So Saidzev rule definition you should prepare, question can be asked from here. Next, reactions with metals, it is very simple. First one is your Grignard reagent, Rx plus Mg will give you RMgBr, which is called as Grignard reagent, and you should remember that it is always, as we have discussed, as we will discuss in the question, it always required anhydrous medium. Okay, it is always requires anhydrous medium, or there should be no water. Why? Because you see this one is giving you RMgX, right? This R minus Mg plus, this is highly reactive. If it finds any proton, okay, in the medium anywhere, it will immediately react to give you RH. Okay, so that is why to keep the Grignard reagent in the form of Grignard reagent, you should have no aqueous medium at all. Next, coming to Woods reaction. Woods reaction, what is there? Simple, Rx plus Na will give you RR plus NaX. From Woods reaction, you also have here Fittig reaction, right? Fittig reaction is what? You have aromatic halogen like this, you will get diphenyl. And Woods fittig is also there, Woods fittig. In Woods fittig you have one RX and one ARX to give you RAR. Okay, clear? Okay, now we have the chemical reactions of haloarenes. This is important. So first we have here nucleophilic reactions, electrophilic substitution and reactions with metal. Now under nucleophilic substitution reaction I'll tell you what is there, and under reactions with metals we have same Grignard reagents and Woods fittig, not Woods reaction, this is actually fittig reaction. Okay, fittig reaction here. Okay, now if we see the first of all that haloarenes, okay, nucleophilic substitution, haloarenes are less reactive. This is a very potential question where many times it is asked that haloarenes do not show nucleophilic substitution reaction, that is why they show electrophilic substitution reaction. So what is the reason why they do not show this nucleophilic substitution reaction? This is very important question. You can see here the first one is your resonance effect, second is difference in the hybridization of the carbon, third is the instability of the phenyl cation. Okay, so to mention the reasons and the explanation for that. So just I'll explain. For example, if you have this RX, right, you have this X group, it has lone pair, here there will be resonance. So if the reaction has to happen, what will happen? Nucleophile has to attack here, the X has to go, and we will get RNU, right? We will get this one, but this reaction does not take place because this nucleophile, this bond is having a partial double bond character. Because of this resonance, see, I'll remove. Okay, now see, because of this resonance what happens, this one forms a partial double bond character. When double bond is there, the bond is very strong, so nucleophile cannot just remove this X like that. Okay, that's the first thing. Second reason was difference in the carbon hybridization. This carbon is sp2 hybridized. Sp2 hybridized means it is more electronegative, so this bond is again very strong because of the sp2 hybridization of the carbon. The third one is the instability of phenyl carbocation. In case suppose you have put so much efforts and somehow you remove this X, then we will get a carbocation, right? We'll get a carbocation, phenyl carbocation, and this carbocation is highly unstable. So it does not want to go to this unstable state, so that is why this reaction is also not possible. Okay. Now we will see the first, that is nucleophilic substitution reaction. You can see if I just take simple chlorine and NaOH. So here the nucleophile is OH, OH will replace Cl. So I told you it is very difficult. Then how is it happening, ma'am? It is happening at a very high temperature and a pressure. You can see 623 Kelvin and 300 atm pressure. If you give that much, then only this reaction can happen. Then what we can do? See, what is the problem? The first of all, if you see, nucleophile is electron rich, right? And yes, and this ring, because it is donating electrons, we have we have double bond or double bond loosely bound electrons. So this ring itself is also nucleophilic. Okay, so a nucleophile cannot react with another nucleophile. The one thing what we can do is we can make this ring more electrophilic in nature. So for that, if you add any electron withdrawing group, you can see the reaction is now taking at 443 Kelvin. If you add two withdrawing group, it is taking place at 368 Kelvin. If you are taking at you are adding 3 NO2 group, then you can just do the reaction with warm water. Okay, so that is the thing you should remember. Actually it is not possible, but at very high temperature and pressure it is possible, or else if you just add electron withdrawing groups, then also it is possible. Okay. Next we'll go to electrophilic substitution reaction. So here we have the first one is your halogenation. Okay, so you should remember the reagent. So chlorine with FeCl3, and here I told you it has to be dark. Okay, so that one will replace, or you will get chlorine at ortho and para position. So X is what? Ortho and para directing, because it is electron donating in nature. Next we have concentrated HNO3 and H2SO4. This is your nitration. You will have NO2 at ortho and para position. Third one is sulfonation, concentrated H2SO4. You will get SO3H, SO3H at ortho and para position. Next we have Friedel-Crafts acylation, CH3COCl, AlCl3, this one will also give you ortho and para substitution. Then Friedel-Crafts alkylation, this one will also give you ortho and para substitution. Okay, so this was very easy, electrophilic substitution reactions. Next we have, okay, so yes, that's all the reactions of your haloalkanes and haloarenes. Now we will move towards solving the questions. Okay, so I brought you 20 questions. Let us start solving them. Very high. Okay, so now let us try this first question. You have bromoethane, bromoform, chloromethane and dibromomethane. So first of all, if you see, you have one carbon in all of them, right? All one carbon is there. Now coming to bromine. Bromine, here we have 3 bromines. Bromoform means CHBr3. You have 3 bromines, so definitely its mass will be high. Its boiling point will be highest because its mass is highest, right? So I can write for the first one, bromoform will be the maximum one. You have to write increasing order. Increasing order means what? Lowest to highest. So this is the highest one. Then you see here bromomethane, here dibromomethane. Dibromomethane means 2 bromine is there, right? So I can write here dibromomethane. Okay. Next what we have, bromomethane. Bromomethane. Next we have here bromo from chloromethane. Okay, chloromethane. Clear? Now coming to the second one, 1-chloropropane, isopropyl chloride and chlorobutane. So if you see 1-chloropropane, isopropyl chloride and chlorobutane, definitely here we have 4 carbons, its mass will be more. So the highest one will be 1-chlorobutane. Without any confusion we can write down this one. Now here if you see isopropyl chloride is like this. This is isopropyl chloride and 1-chloropropane is like this. So you see here there is a branching, here it is a straight chain. So I told you branching is more means boiling point will be less. So what I can write here, it is isopropyl chloride. Okay, and then here it will be 1-chloropropane. Clear? Done? Now we will go to next question. Okay, which alkyl halide from the following pairs would you expect to react more rapidly by an SN2 mechanism? Explain your answer. So SN2 mechanism, if you remember, what does SN, so let me just explain in this previous slide. Here some blank space is there. Let me explain here about SN2. See, SN2 mechanism will always follow less crowd. Okay, less crowd, or you can say small molecules. Small molecules will undergo SN2 mechanism, and that is why the order here is 1 degree, 2 degree and 3 degree. Okay, SN1 is more about carbocation stability. Carbocation stability. More is the carbocation stability, better will be the reaction. Okay, so generally carbocation stability is 3 degree, 2 degree, 1 degree, but it is not always. If you have some resonance stabilized carbocation, that is given more priority. So what is here before that? Resonance stabilized carbocation. Okay, so now if I move here, so we want from SN2 mechanism, right? So you can see here this is primary, this is secondary, so definitely primary will react faster. So the first one here. Next here you see this is secondary and this is tertiary, again secondary will react because of less bulkiness. The third one, if you see that this is also primary, this is also primary, but here what will happen, this branching is very closer, right, and here the branching is little farther. So I can say that near this bromine, the steric, so the nucleophile has to come and attach on this carbon, right? So you can see this CH3 is far away, so its impact is less, and here it is near, so it will create more impact here. So here the disturbance will be more, so here the first one will be the one which will react faster. Reason you can write down for all of them, because of less steric hindrance. Because of less steric hindrance. Clear? Now here the question is from SN1. So SN1 we know 3 degree, 2 degree and 1 degree. So this is 3 degree, this is 2 degree, definitely this one. Here what we have, this is 1 degree, this is 2 degree, so definitely this one. Okay, and what is the reason here? You can write down because of stable carbocation. Okay. Now we'll go to question number 9. Identify A, B, C, D, R and R1 in the following reactions. Okay, so let us do this. So Mg and Br, this is our Grignard reagent. So what will be A here? A will be MgBr. Okay, now what will happen when you put water? Okay, then water, when you give water here, this one will get converted to hydrogen. Okay, so that is why you can see this is R minus, this is plus, and we have H plus and OH minus, right? This minus will attack on this H and you will get here H. Okay, cyclohexane will be produced. Next we have again here, I will get RMgBr. Okay, okay, just a minute. You have to identify C also. Okay, so first I will get CMgBr, then if you see this one is getting attached here, right? So that means okay, we have to try this doing like this. So if I think that it is like this, CH3 CH3 Br is like this. Okay, suppose this is like this, then if you give here Mg ether, okay, Mg ether, dry ether, if you take, this one will be added here Mg. So I will get CH3 CH MgBr and CH3. This is there. After this what happens? Here D2O is there, means D plus and DOD minus I can write. So this C, right, this is plus and this is minus, this one will attack here. So what I will get, this part will be replaced with D. So that is why I'll get here. So what is this then? This you can easily guess here. This has to be okay, this has to be color. Okay, this has to be this one, that is CH3 CH3 MgBr. Okay, so this is plus, this is minus, this minus will attack on D and we will get this one. Okay, next we see here we have R1X, and if you treat it with Mg, so first I will get here R1 MgX. Okay, next if I treat it with water, again this one will get, and I will get R1 and H. Okay, but I have to find what is the structure of R1, so we will do that, do not worry. Now if you see R1X has here, this is your Woods reaction, so it is like exactly the replica, so I can say that Rx is nothing but CH3 CCH3. Let me write down it properly like this. This must be CH3 CCH3 CH3 and X, right? So this is your XR group, so that's why it will react very easily to give you this one. Here X you can take anything, you can take chlorine, for example, chlorine, bromine, anything you can consider, right? Just a minute. Yes, clear? So then what will this one will become? This one will become the, you have to just replace this one. So this here Mg will come. So I will get CH3 CCH3 CH3 Mg, and if I take in Cl it will become Cl. If you have taken Br it will come Br. Next what will happen? H2, here H will come. So I just have to replace this one. So I will get E as sorry, just a minute. Yeah, I will get CH3 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 and here H will come. Clear? Done this one? Okay. Next, question number 10. Which one of the following has the highest dipole moment? This is very important question. This is from your exercise question number 6.4. Okay, so I have not taken all the questions, but important questions I have taken. So if I draw the structure of this one, CH2Cl2, it is like this. Okay, CHCl3. Then I have CCl4. Okay. Now if you see, dipole moment means what? Towards the more electronegative atom. So this dipole moment is in this direction, this is in this direction, this is in this direction, and this is in this direction. So there is a net dipole moment towards this direction. Okay, there is a net dipole moment towards this direction. Now here what happens, this is in this direction, this is in this direction, this is in this direction, but this is in opposite direction. So the net dipole moment decreases here. And here what happens, you can see this is in this direction, so we will have a net dipole moment in this direction. Similarly here a net dipole moment in this direction. So the total magnetic moment here becomes 0. Here it is somewhere around 1.6 and here somewhere around 1.3. Okay, so which one is the highest one? That is your first one is highest because of, how will you write? Because the net dipole moment is in the same direction. Clear? Okay, next we'll move to question number 11, that is explain why the dipole moment of chlorobenzene is lower than that of cyclohexyl chloride. So if you compare chlorobenzene, that is, this is chlorobenzene and this is cyclohexyl chloride. So what happens, this carbon, the electronegativity difference, more is the electronegativity difference, better is the dipole moment, right? But here what happens, this is sp2 carbon, it is very highly electronegative. This is sp3 carbon, which is less electronegative. So here the electronegativity difference between the carbon and the chlorine is more, so it is more dipole moment, or it has higher dipole moment. How can you write? The dipole moment of chlorobenzene is lower because the CCl bond in chlorobenzene is less polar. This is less polar. Why? Because the carbon in chlorobenzene is sp2 hybridized. Okay. Next, alkyl halides, though polar, are immiscible in water. So if you see Rx, okay, this is delta minus and this is delta plus, they have a polarity in their bond, and water is also a polar solvent, and we know that polar dissolves polar. Then why is that haloalkanes not soluble in the water? So for that you have to understand the mechanism of dissolution. So what happens, the bond between these two, okay, the bond between these two should break and the bond between the R and the water should form. Okay, the bond between Rx should break and the bond between R and the water should form, so that it is soluble. But exactly what happens here, see, in order to dissolve the haloalkane in water, energy is required to overcome the attractions between the haloalkanes molecules and break the hydrogen bonds between the water molecules. We need some, suppose these are two haloalkanes, okay, so there's a force of attraction between them. We need some energy to break this attraction and we need energy to form bond between this one and water. So what happens here is, the less energy is released when the new attractions are set up between the haloalkanes and the water molecules. When see, you have to break this two bond and you have to form this one bond between haloalkane and water. So when you are forming this bond, how much energy is released? That should be equal or enough to break the bond between two haloalkanes, right? So here what it is saying, that the energy, less energy is released when the new attraction is set up between the haloalkane and the water molecules, as these are not as strong as the original hydrogen bond in water. I hope you might get confused. Let me explain. See, this is one, I am writing Rx, okay, and this is one water molecule. So there is some force of attraction between here, and we have to form a force of attraction here. So for a solubility, what should happen? This attraction should break and this attraction should form. So when this attraction is forming, okay, when this attraction is forming, their energy will be released. Energy is released. Now whatever energy is released should be sufficient to break this bond. okay, but that does not happen. Why? Because the energy released is low here. Why it is low? Because here water interaction is very high. So why will water try to break or form bond here when this bond is very strong? Understood? So that is why the energy released during the haloalkane and water bond is very less compared, or is not enough to break the haloalkane bond. Okay, so that is what is given in the book. You should write down this particular thing. Next, Grignard reagent should be prepared under anhydrous conditions. So here the answer is Grignard reagent. If you see, it is RMgX, right? This is minus. If it finds any H plus in the medium, any H plus, proton from any H plus, especially from water, if you see, water is what? H plus and OH minus. So what will happen? This one will react with this one and we will get RH. We will not be able to do the reactions that we want. Grignard reagent will immediately get converted to haloalkanes. So to prevent that, we should take in the anhydrous medium. So Grignard reagents are highly reactive and react with any source of proton to give you hydrocarbon. It can react with any source of proton. It is therefore necessary to avoid even traces of moisture from a Grignard reagent. That is why the reaction is carried out in dry ether. Clear? Okay, this is very simple. Next we'll go to, so this was my question number 11. It's a 6.12 question from the book, but in this series this is 11th question. Okay, I have explained this one. Next we have to do some questions, quick revision. So these type of questions help you to revise the reactions more. So first of all, if you see, this is what your Finkelstein reaction, dry acetone. So what will happen? Chlorine will replace with iodine. So product here will be CH3, CH2, CH2I. So this is your 6.14 from the book. Now CH3, whole 3, Br and KOH, ethanol and heat. So you have given alcoholic KOH. See, when you have aqueous KOH, substitution takes place. If you have given alcoholic KOH, elimination will take place. So this one, if I want to show you here, so it is like this: CH3, C, CH3, I have H here, sorry, I have Br here, and I will write this one like this. Okay, so when I give this alcoholic KOH, this one will be removed and a double bond will form here. Okay, so what I will get? I will get here CH3, C, CH3, double bond CH2. Okay, next we have Br and NaOH water. So what will happen? This is your aqueous NaOH. So there is nothing happens, simply this Br will be replaced with OH. So I will get product here CH3, CH, OH, CH2, CH3. Okay, next here we have aqueous KCN. This is also simply replacing this Br with the Cn, right? So we will get here CH3, CH2, Cn. Okay, next here you have C6H5ON and C2H5Cl. So this is your what I'll say, that is your Williamson ether synthesis, right? So what happens here? This one will attack on this one, right? And this one will go out and you will get C6H5O minus and this side, right? So I will get here like this product I'm extending here. So it will be like C6H5, okay? Then O is there, then CH2 and CH3. Next we have SOCl2. It will simply replace OH with the Cl. So I will get CH3, CH2, Cl. Okay, next when you have peroxide with HBr, it is your anti-Markovnikov's rule. Bromine will be added here. So you will get CH3, CH2, CH2 and CH2Br. Okay, next here you have taken HBr, only HBr without any peroxide. So what will happen here? It will follow Markovnikov's rule. Br will go to the carbon having less number of hydrogen. So here I have less number of hydrogen. Bromine will be attached here and H will come here, and the product formed here will be, I can write like this, CH3, CH, okay, then here I have C, CH3, CH3, Br, and H2. Okay. Next we have question number 13. Out of C6H5CH2Cl and C6H5CH Cl C6H5, which is more easily hydrolyzed by aqueous KOH? So basically what happens, if you have Rx and if you treat it with aqueous KOH, you will get ROH. Okay, so the question here is, you have C6H5 CH2Cl, okay, and you have one more C6H5, okay, CH Cl C6H5, right? Now what happens, the question here is, if both of these are reacted with aqueous KOH and aqueous KOH, then which one will react faster, this one or this one? Okay, so for this, the first thing you should be knowing that this reaction takes place by SN1 mechanism. If SN1 mechanism is there, that means what? It means that carbocation formation will take place. So what will happen here, the carbocation will form, okay, and next thing is here the carbocation will form, right? Two carbocations will form. Now which is more stable? So here you see it is stabilized by only one group which can donate electron resonation, and here you can see two groups are there which can stabilize it by resonance. So what will happen? Basically this carbocation is more stable, so it will form faster and it will react faster. Okay, so answer is like this. You can see here that hydrolysis by aqueous KOH takes place by SN1 mechanism. The C6H5CH2Cl or benzyl chloride gives you this carbocation. I have written it 1 here so that next time whenever I write, I can represent it as 1 carbocation, while C6H5CHCl C6H5 generates this carbocation. Now out of 1 and 2, 2 is more stable due to resonance, and this carbocation is formed easily, and hence C6H5CHCl C6H5 is hydrolyzed easily. Clear? This is very important question. Next is question number 14. In haloarenes, para isomers have the higher melting point as compared to their ortho and meta isomers. Why? So this is there in your NCERT question as well and previous year question also. Yes. So what happens? The para dichlorobenzene, okay, or any para haloarenes, they are more symmetrical. Okay, if they are more symmetrical, they will fit better into the lattice. So that is the thing. For this reason, it fits more closely than ortho and meta in the crystal lattice. Therefore, more energy is required to break the crystal lattice of para dichlorobenzene. As a result, para dichlorobenzene has a higher melting point and boiling point and lower solubility than ortho and meta isomers. Okay, so that is the structure here. Next, the treatment of alkyl chloride with aqueous KOH leads to the formation of alcohols, but in the presence of alcoholic KOH, alkenes are the major product. Explain. This is a very important question. So the question here is very simple. I'll take one example and explain. The question is like this. If I have this one and if I treat it with aqueous KOH, Cl will be replaced with OH, right? And here I am treating it with alcoholic KOH. So here H and Cl will be removed and we will get one alcohol here. Okay, this is the thing. Clear? Now the question here is telling what happens if you just take aqueous and alcohol, right? Means what you are telling, you are taking KOH here in the water and here you are taking KOH in an ethanol. Okay, so what exactly is happening, that this reaction is completely changing. So here you see, when you have taken this one, this is existing in the form of K plus and OH minus. Okay, now OH minus is completely surrounded by water molecules. Okay, it is because aqueous molecule, it is completely surrounded with water molecules. Now due to the complete solvation or hydration, this OH minus basicity decreases. Basicity is decreasing and it behaves as a nucleophile. It is no more a base. So here basically what we are doing, see, if you see this part, here any base is there, base is abstracting this hydrogen, this bond is coming out and this is left, right? So whatever is generated, X, Y, Z, that is behaving as a base. So here OH minus cannot behave as a base because it is completely hydrated, and it behaves as a nucleophile and it removes the chlorine and itself it get attached. That is the substitution reaction happens. But when you have alcoholic KOH, like for example I write C2H5OH in presence of K plus and OH minus. So what will happen? Here this one forms water molecule, okay, and this one exists like this, C2H5O minus and K plus. Now this O minus and K plus, this one RO minus is a very good base. Okay, so this one can abstract a proton and the elimination reaction can take place. Okay, so that is the concept. And how can you write it? So in an aqueous solution, KOH almost completely ionizes to give you OH minus ions, a strong nucleophile, and reacts with alkyl halides to form alcohols. In an aqueous solution, the OH minus ions are highly hydrated. This reduces the basis character of OH minus, due to which they fail to separate the hydrogen atoms from the beta carbon of alkyl halide. Okay, and they cannot form an alkene. On the other hand, the alcoholic solution of KOH contains alkoxide ions, which being a stronger base than OH minus easily removes the HCl molecule from the alkyl chloride to form alkene. So here, as I said, when you take alcoholic KOH, you generate this species, that is RO minus, which is a very strong base as compared to OH minus. Okay, clear? Now we will go to question number 16. Yes, this question is very important. Primary alkyl halide C4H9B are reacted with alcoholic KOH to give you compound B. Okay, so I have C4H9Br which reacted with what? Alcoholic KOH to give B. So if alcoholic KOH is there, means there is elimination, and I can guess that this has to be an alkene. Okay, now compound B is treated with HBr, okay, to give compound C, which is an isomer of A. So if you see here one alkene, then HBr will be added, so definitely there is the here Markovnikov's addition will take place, so that is why it is an isomer of A. Okay, next, when A is reacted with sodium metal, when A is reacted with sodium metal, it gives compound D. Okay, it gives compound D, that is C8H18, which is different from the compound formed when N-butyl bromide is reacted with sodium. So you can see sodium and metal is nothing but Woods reaction. So if you are taking N-butyl bromide, okay, N-butyl bromide, that is like this. This is your N-butyl bromide. And one more thing, if in this formula C4H9Br, what all possibilities are there for primary alkyl halide? One is your N-butyl bromide, that is this one. Okay, this is one possibility. Another is like this. I'll put here, just a minute, I will put here oh sorry, I wrote the wrong structure, just a minute. I want to write the chain structure like this, CH3 CH CH3 CH2 Br. Okay, so now you see this is also primary, this is also primary, but this statement says that when A is reacted with sodium metal, it gives a compound D, which is different from the compound formed when N-butyl bromide is reacted with sodium. So that means definitely A is not N-butyl bromide, so A has to be this one, right? So we have already found now our A. Okay, so A is this one. Then give the structural formula of A and write the equations for all the reactions. Okay, so I have got already A, so I will now write down the reactions. What is my A? I got CH3 C CH3HCH2Br. This is A. Now if I am treating it with alcoholic KOH, here HBr will be removed, a double bond will form, so I will get CH3 double bond CH2. Next, if I treat it with HBr, what will happen? Markovnikov's addition will take place, bromine will be attacked here. Okay, so this is your A, this is B, and this is C. Next, what is there? Compound D. So now if this one is reacted with sodium or Woods reaction will happen, so we will have a product like this, CH3 CCH3 CH2. Okay, I'll write H here, CH2, then here again this one is connected to like this. Okay, and this one is your sodium and ether. Clear? Okay, next question number 17. What happens when? So these are some reaction based questions, so I am giving you more reaction based questions so that we can prepare. N-butyl chloride is treated with alcoholic KOH. So we have here N-butyl chloride, means I will write like this. So let me write it from the left hand side corner so that I can have space. So I will write 3 on this side and 3 on this side. Okay, so we have N-butyl chloride, CH3 CH2. I will write this one knowingly like this so that I can show you when I have alcoholic KOH, there will be elimination and I will get the product like this. Okay, next we have the second one, that is bromobenzene is treated with magnesium in presence of dry ether. So if I have bromobenzene, it is treated with magnesium, presence of dry ether. So we will get a Grignard reagent here, that is MgBr. Now third one is what? Chlorobenzene is subjected to hydrolysis. So if you have chlorobenzene, okay, now you see chlorobenzene hydrolysis is not easy. It takes place at a very high temperature and a high pressure, so 300 atm and 623 Kelvin. If you heat it with NaOH, so this Cl will be replaced with OH and I'll get like this. Okay, next we have the fourth one, and it is ethyl chloride is treated with aqueous KOH. So we have ethyl chloride, sorry, here we have ethyl chloride is treated with aqueous KOH. So chloride is replaced with here alcohol. Okay, next fifth one is methyl bromide is treated with sodium in presence of dry ether. Methyl bromide is treated with sodium in presence of dry ether. Okay, so what will happen here? It is your Woods reaction, so I will get ethane. Okay, next I have sixth one, methyl chloride is treated with KCN. So methyl chloride is treated with KCN, so that will replace Cl with Cn and you will get CH3CN. Clear? So this is what the products will form. Very easy question. Next, your name reactions. So these are the name reactions in this chapter you must prepare. Schwartz reaction, Finkelstein reaction, Woods reaction, Woods fatigue, then you have Sandmeyer reaction. Okay, so Schwartz reaction, you can, whenever a name reaction is asked, you have to first write down the statement and then the reaction. So alkyl fluorides are synthesized by heating alkyl chloride or bromide in the presence of metallic fluorides such as AgF, HgF2, COF2 or SbF3. This reaction is termed as Sandmeyer reaction. Okay, next coming to Finkelstein reaction. Alkyl iodides are prepared by the reaction of alkyl chlorides or bromides with NaI in dry acetone. This reaction is called as Finkelstein reaction. So here you can mention dry acetone. Okay, Next we have Woods reaction. So alkyl halides when treated with sodium in dry ether gives compound where, sorry, just a minute. Okay, so alkyl halides when treated with sodium in dry ether gives compounds where two alkyl groups are joined together, and this is called as your Woods reaction. So I'll give an example here. You can take like this CH3Cl, and you have here sodium in dry ether. Okay, so that will give me CH3CH3. Next we have Fittig reaction. So aryl halides when treated with sodium in dry ether give compounds where two aryl groups are joined together. It is called Fittig reaction. So you have an aryl halide, sodium and dry ether, and then you treat it with diphenyl to give you, when you get the product diphenyl and NaX. Next you have here Woods Fittig reaction. So aryl halides when treated with alkyl halides in sodium and dry ether, alkyl arenes are formed, and this is called as Woods Fittig reaction. So you have an aryl and you have an alkyl, you react them, you get alkyl arenes. Next you have Sandmeyer reaction. So aniline reacts with dilute nitrous acid to form benzene disonium chloride, which reacts with CuCl or CuBr to give you aryl chloride or aryl bromide. This is Sandmeyer reaction. So okay, I have not given you the reaction, we can write down here. So if you take first aniline, okay, then react it with nitrous acid, you will get benzene disonium chloride. Then you can treat it with CuCl or CuBr. This one will give you chlorobenzene. Okay. Next we have question, aryl halides are less reactive towards nucleophilic substitution. We have already understood. Here what happens in case of aryl halides, there is a partial double bond. So basically what happens, see, if you want, this is suppose aryl halide and you are reacting it with nucleophile. So what will happen, this one will attack here and this bond will go out, right? So I will get here a nucleophile, right? So now what happens if this is the reaction that is happening? So now what happens, this bond, okay, due to the resonance, this bond is very strong. It is not easy to break this bond, and simply the nucleophile cannot come and replace this one. That's the first thing. This is a partial double bond character. The second thing here is the sp2 hybridization of this carbon. Because it is sp2 hybridized, this bond is, this attraction between these two is very strong. Okay, so that is why also it is not easy to replace this one. So you can write it like this, resonance effect. So due to the resonance, the CX bond has a partial double bond character, and due to the sp2 nature of carbon in CX bond, it has more S character and hence holds the bond very strongly. Okay, last question. Chloroform is stored in closed and dark colored bottles. Why? Okay, so you can see here chloroform, that is CHCl3, is slowly oxidized by the air in the presence of light to a poisonous gas, that is COCl2, also called as phosgene. Okay, so 2CHCl3 plus O2 gives 2COCl2 plus 2HCl. This compound is your phosgene. So that is why to prevent this reaction, we store it in the dark bottles. Okay. So yes students, these were some of the important 2 and 3 marker questions from this one. I haven't discussed SN1 and SN2 question because as I told you, there's an important 5 marker session will be coming where I'll be taking all the 5 marker questions. Okay, so yes, now we will be doing the next chapter, that is alcohols, phenols and ethers. So students, now we have completed haloalkanes and haloarenes, and now we are diving to the next chapter, that is alcohols, phenols and ethers. So as I told you, this lecture we will quickly revise all the reactions. I'll be giving you the in-text questions, solved in-text questions, then some reasoning questions from the exercise questions. Okay, the 5 marker question I'll make a separate video where I'll be discussing all mechanism 5 marker questions, so do not worry for that. That one video, if you watch, the complete 5 markers will be done, but here there are some 2 marker 3 marker questions which may be asked, so we have to prepare for that. Okay, so the first thing here is your preparation of alcohols, phenols, chemical reactions of alcohols, phenols, then chemical reaction of phenol is very, very important. Then we have preparation of ethers and chemical reactions of ethers. Okay. Now let's start here. The first one, preparation of alcohol. So as I always tell you, read horizontally. First you should have a clear understanding of what all mechanisms or preparation methods is there. First one is from alkenes. Okay, second one from carbonyl compounds, third one is from Grignard reagent. Now these two are not very different. Okay, Grignard reagent also acts on carbonyl compounds to give you alcohols. Okay, so first one, if you see alkenes, we can have acid catalyzed hydration and hydroboration oxidation reaction. Okay, I'll be explaining both of this. Then from carbonyl compounds, how can you prepare from carbonyl compounds? By reduction of aldehydes and ketones, reductions of carboxylic acids and esters. Very, very simple reactions. We do not have to do much things here. And then from Grignard reagent. So if Grignard reagent acts on this carbonyl compounds, we will get alcohols. Okay. So now coming to the first one from alkenes. Okay. So here you remember, suppose I'll take propene as an example here. Okay. If you add H plus and H2O, what will this do? This will add OH and H following Markovnikov's rule. Okay, Markovnikov's rule, what will happen? OH will go to the carbon having less number of hydrogen. So I will get propane, or I'll write the structure, I will get propane 2OL, right? So that is CH3, CHOH, CH3. Clear? Now coming to this one, if you use hydroboration oxidation, it will follow anti-Markovnikov's rule. Okay, so what will happen here? OH will attach here, H will attach here. So I will get CH3, CH2, CH2OH. Okay, clear? Understood the difference? The first one is from alkenes. Second one is from hydrocarbons. So from hydrocarbons you can have the first one using aldehydes and ketones. So wherever, this is very simple, suppose I have CH3, C double bond O CH3. So what will happen if I use hydrogen palladium or NaBH4, this group, this one will get converted to OH. Okay, and then one valency will be free, so that you can balance with H. Then similarly you can have here acids and esters. You have to use lithium aluminium hydride and hydrogen and palladium. Okay, when we'll do questions we will get to know this reaction, so do not worry. Second one is the Grignard reagent. This is important one. Sorry, not the second one, this is the third one. So here what happens, this is Mg plus and this is minus, so this R minus attacks on this one, this bond shifts here and we get alcohol. Clear? So about Grignard reagent I want to tell you, so if you have RMgX, okay, and you take HCOH, what will I get? This is R minus, right? This will attack on this one, this bond will shift here. So after that, here what will happen? You see H, C, here O is there. First you will get OMgX. This is O minus, this is plus, right? So please understand this mechanism. Grignard reagent questions are asked repeatedly. Okay, so what will happen? O minus and C plus will be there. This one will attack here. This O minus will take Mgx, and then this side also I have H and this side I will have R. Then after, if I do hydrolysis, okay, or I'm just writing here, if I do hydrolysis, what will happen? This OMgX will get converted to OH. So which type of alcohol I am getting? You can see this carbon containing the alcohol is attached to only one carbon, so this is a primary alcohol. Now if I take RMgX, okay, with any other aldehyde, like for example CH3, C double bond OH. So what will happen? R dash will attack here, this one will become OH and this one will become H. So I will have CH3, C, OH, R dash and H. Okay, now if I have again R dash MgX and you have ketone, that is CH3, CO, CH3. So this is what? Secondary alcohol. Why? Because the carbon is attached to, the carbon containing the OH group is attached to two other carbons, right? Now here what will happen? This one will attack here, this one will attack here, you will get OH here. So I will get CH3, C, OH, CH3 and R dash. Okay, so you will get a tertiary alcohol here. Clear? So the basically I want to say you that if you take formaldehyde you will get primary alcohol, if you take any other aldehyde you will get secondary alcohol, and if you take acetone or any ketone you will get tertiary alcohol. Okay. Now we have here, so we will see the next thing, preparation of phenol. So here so many reactions are there. The first one is from haloarenes. Okay, this we have already discussed last in the haloalkanes chapter. With very high temperature and pressure we can get haloarenes. Then from benzene sulfonic acid, that is the oleum reaction that we will discuss. From disonium salts, that is also a very important process. Next from cumene. So this is very important one, from where questions have been asked repeatedly. So from this is very important, you must prepare this one properly. Okay. Now if I see quickly the mechanism, that is from haloarenes, the first one. So at NaOH at very high temperature and pressure, because there is no electron withdrawing group, we will get phenol. The second one from benzene disonium chloride, NH2 is there. First you can convert it to N2 plus Cl minus, that is benzene disonium chloride. Then you use warm water, here OH N2 plus will be replaced with OH. Okay. Next, third one we have is, this is from your benzene sulfonic acid. Okay, you convert it into, so this is from your sulfonic acid. Okay, so first of all you get benzene, convert it into sulfonic acid, then treat it with NaOH and H plus. This one will be replaced with OH group. Next is your oleum one, your cumene one. This is very important process, so please practice this one properly. Just read the NCERT book, its statement properly. Okay, so when you take isopropyl benzene, this is called as cumene or isopropyl benzene. You should know the name as well. Okay, cumene or isopropyl benzene, treat with O2. What will happen here? This H is there, this O2 are inserted. Then H plus and H2O, if you take, this OH will attach here and this one will form your acetone. So you will get phenol plus byproduct is acetone. Okay. Okay. Now we will move to the next one, that is reactions of alcohols. Preparation over for both. Now under reactions of alcohols we have certain types of reactions. Okay, so first of all I will explain some basics about that, understand it quickly. Reactions of alcohols, we have one, this is group, right? So acids, it can break this H plus, or this bond can break, and we will get RO minus and H plus. Okay, now this RO minus is a very good nucleophile and it can react with many things to give you different reactions. That is one possibility where this cleavage of OH bond is taking place. This is one type of category of reaction. Second category of reaction is where this RO bond will break. Okay, how will this RO bond generally break? So generally when we have an acidic medium, okay, so this one will take this H plus, this gets converted to RO plus H2, then this one will remove and we will get R plus. So generally here you see this is behaving as a nucleophile and here this will behave as an electrophile. So based on two of these properties, the reactions of alcohols are cleavage, where we have, reactions of alcohols are divided or classified. One is cleavage of OH bond, another is cleavage of RO bond. Okay, so now we will see the reactions. The first one is cleavage of OH bond. So in this it will behave as a nucleophile, right? It will behave as a nucleophile. Cleavage of CO bond, here it will behave as an electrophile. Here the first one is reaction with metals, acidity of alcohols and esterification reaction. Okay. Next here we have cleavage of CO bond. There we have reaction with HX and reaction with PX3. Okay. Simple. Next we have dehydration reactions and then we have oxidation reaction. Okay, four types of reactions are there under this. The first one, reaction with HX, reaction with PX3, reaction dehydration, and then we have reactions or oxidation reaction. So let us first understand this one. So if you see, just a minute. Okay, so if you see here, the first one, that is cleavage of OH bond, here I am getting RO minus. Okay, now if this one is reacting on any metal, RO minus and Na plus, so what will happen? This H will go out. Sodium is a metal, so RONa will form, okay, with H2 gas produced. That's the first thing, that is reactions with metal. Reactions with metal. The second one is your esterification reaction. So see, ROH, or I can write RO minus, can react with three things to give you esters. The first one is your acid, second one is acid chlorides, okay, acid chlorides, and third one is anhydrides. Anhydrides mechanism you don't have, it is not asked, but so basically you have to understand like this. Here RO minus is there, it will attack on this one and this bond will break. Okay, so you will get RCOH. So this is your ester formation. Similarly with anhydrides, similarly with your acid chloride. So quickly let us see here. Suppose I have this one RO minus, okay, and if it is reacting with any acid, so what will happen? So this one will attack on this one will come, this bond will go, and you will get RCO. So I am writing R1, R2. So I will get R1 C double bond O and OR2. Okay. Similarly, a mechanism is not required. Here we can have Cl, here we can have the other OR group in case of anhydride. Okay, so don't waste your time in this mechanism, but you should remember for esterification we have three reagents. One is acid, acid chlorides, and anhydrides. Next we'll go cleavage of CO bond, right? Under cleavage of CO bond, first one is the reaction with HX. Here what will happen? O plus H2 will go and then XRX will form. This is your Lucas reagent. So if you remember ZnCl2 and HCl, this is your Lucas reagent, and here you should remember the tertiary one will react the fastest, okay, secondary one will react after 5 minutes, okay, and primary one will not react. So this can be used, what Lucas reagent can be used as a test for alcohols. Which degree alcohols it is, primary, secondary or tertiary, we can easily find out using this reagent. Second one, PX3, this we have already studied, right, in your haloalkanes chapter. ROH plus PX3 will give you what? RX. Okay, so here what will happen? This one OH is there and it is having RX, this OH will be replaced with X and we will get RX. Okay. Next we have here dehydration reaction. So you have H2SO4 at 443 Kelvin or H3PO4 you can use. So dehydration will take place and we will get alkene as the major product here. Okay. Now dehydration is also the order of the dehydration is 3 degree, 2 degree and 1 degree reaction. Okay, clear? This is done. Now we have the oxidation part, cleavage of CO bond, oxidation reactions. So the first one is your CrO3, oxidizing agent. In this, primary alcohols will be converted to aldehydes, secondary alcohols will be converted to ketones. Now the second one is your PCC. In PCC what happens? Primary alcohols gets converted to aldehydes. And the third one we have here is copper at 573 Kelvin. Here also primary will convert to alcohols, aldehydes, secondary will convert to ketones, and tertiary, very important, tertiary will give you alkenes. Okay, here tertiary will not react, here tertiary will not react, but copper at 573 Kelvin will react and give you tertiary alkenes. Okay. Next, reactions of phenols. This is very, very important. We have so many reactions under this one. So let us quickly see. The acidic nature I will explain for both alcohols and phenols together. So this you can leave for now. Esterification reaction we will discuss. Electrophilic substitution reaction, Coles reaction, Reimer-Tiemann reaction, reaction with zinc dust, and oxidation. Okay. Under electrophilic substitution we have, okay, so acidic nature we have reactions with Na and NaOH. Okay, so the question can be asked, write any two reactions which show the acidic nature of phenol. Write any two reactions which show the acidic nature of phenols. Then you can write reactions with Na and NaOH. Okay, next we have esterification. Under electrophilic we have nitration and halogenation. Okay, very important one. Then we will discuss the first thing, that is reaction acidic nature, right? The first one is acidic nature. I'll discuss about the acidity order in a separate section, but acidic nature, how will you find? So Na and this one, the same thing, what will happen? ONA and H2 gas will form. But here if you have NaOH, so ONA will form, this H and this OH is there, so you will get a byproduct here, H2, that is the difference. Okay, the first one, acidic nature. Second one is what? The esterification process, it is similar to the alcohols. Here we will discuss the second one, that is electrophilic substitution. So I am just writing electrophilic. Under that we have, first one is nitration. Okay, so nitration, if you see dilute HNO3, if you take, you will get ortho and para product separately. Now how are we getting ortho and para product? Because this one is electron donating group, and electron donating group, so it is ortho and para directing group. Okay, so at ortho and para position the substituents will be attached. Next we have concentrated HNO3. If you use it, all the ortho and para groups will be occupied at the same time. Okay, so that is the difference. Nitration 2A, this is nitration 2A. Electrophilic substitution 2B is your halogenation. Okay, now in halogenation, if you just simply use bromine water, then all the ortho para positions will be substituted. Now if you use bromine with the CS2, okay, bromine dissolved in CS2, in that case what will happen? Bromine will come at the ortho position and also at the para position, two different positions it will come. Clear this one? Next we have here the third one is your Kolb's reaction. Kolb's reaction. Okay, so 1, 2, I think this one I am not, this one will be 3. Why? I am taking according to the order I have written on the table, right? So second was your esterification, which I have not discussed here, that because we have already discussed. So third A, and this is your fourth one is your Kolb's reaction. Okay, Kolb's reaction also important name reaction statement, and the reaction you should remember. So first you treat it with NaOH, you will get O minus Na plus, then treat it with carbon dioxide and H plus, you will get COOH, and this product is called as salicylic acid. So please remember, this is called as salicylic acid. Okay. Next, fifth one is your reaction with Riemer-Tiemann reaction. So here CHCl3 and aqueous NaOH, if you use, O minus and Na plus will form here, and with respect to here we will get CHCl2. Then again NaOH if you treat, you will get benzaldehyde, O minus Na plus, H plus, you will get here this one OH and CHO, and this is called as salicylic aldehyde. Okay, and this is your which reaction number? Fifth reaction. Riemer, or how do you pronounce, you can check, it is Riemer-Tiemann reaction. Okay, there may be change in the spelling as well, so please check that. The sixth one is your reaction with zinc dust. So phenol on reaction with zinc dust will give you what? Will give you benzene. And seventh one, Na2Cr2O7, if you treat, oxidation will take place, and this product is called as benzoquinone. Okay, clear? Next we have esterification of phenol. So it is very similar to the alcohols. What? So if you use acids, you can use, here you will get OCOR dash plus byproduct is water. If you use anhydride, you will get same OCR dash, okay, and the another byproduct is another acid, and here also you will get OCOR dash and HCl. But the thing that is important here from where question is asked is your aspirin formation. So you can see if you take salicylic acid and treat it with acetic anhydride, so here you will get OCOCH3, and this compound is called as aspirin, which is used as a drug or a medical product. For medicines it is used. Okay, so these are all reactions of alcohols and phenols. Okay, so just if I want to summarize once, okay, before that let me talk about the acidic nature of phenols and alcohols. So remember, if we have electron withdrawing group, then acidic nature will increase. Okay, if you have electron donating group, acidic nature will decrease. That's what you have to know. Like for example, if I give a question like this, you have one phenol, okay, you have one phenol with NO2 group, okay, and then you have phenol with OCH3 group. Okay, 1 second. Yes, so now you see this is an electron withdrawing group and this is an electron donating group, right? So electron withdrawing group will increase the acidity. So this one will be highest acidic, then this is neutral, and then this is electron donating group, less acidic, right? So what is the acidic order here? 1, 2 and 3. Okay, so this compound is the first one, then this one, and then this one. So that is how you should remember for the acidity order. This is what you should memorize, that electron withdrawing group will increase the acidity, donating group will decrease the acidity. Okay. Now moving forward, we have preparation of ethers. So okay, before that I just want to quickly revise the reactions of phenols. Okay, so if you have OH, reactions of phenols, you see there were 7 reactions. Okay, I have remembered. Quickly we will revise. The first one is acidic nature. For acidic nature we have reactions with Na and NaOH. Okay, products I know, here I will get O minus Na, here also I will get O minus Na. You can also revise with me quickly. So this is the first one, acidic nature. Second one is esterification. For that what all reagents I can use? CH3COCl, CH3COO, H, you can use like acid chloride, acid and anhydride, CH3COO whole 2. Okay, next for third one what I need? Third one I need here is acidic nature over esterification over what was the third one? Electrophilic substitution, right? For that I have dilute HNO3, I'll get separate product. I have concentrated HNO3. See, this is how you should revise, active recall. Okay, don't learn the short notes again, revise it like this. Dilute HNO3 nitration over, then for bromination you have bromine, that will give you all the 3 products, and here you have bromine with CS2. Okay, so 1, 2, 3 over. Then fourth one was what? Fourth one was your Kolb's reaction, right? So in Kolb's reaction, first you have to treat it with NaOH and then you have to treat it with CO2 and H, and what you will get here, the product was salicylic acid, right? Then fifth one was, if I remember, fifth one was your Riemer-Tiemann reaction. So you use there CHCl3 with KOH, then you use NaOH and H plus, and you will get here OH and CHO. Quickly revise with me. Then sixth was your zinc dust, okay, that will give you phenol, and the seventh one was what? Oxidation, that is K2Cr2O7, which is your benzoquinone, right? With you just see with this much we can revise all the reactions of organic phenols. Now we will go to the next one, that is now let's see the preparation of ethers reaction. Under that we have 2 mechanisms, one is dehydration of alcohol, another is Williams ether synthesis. Now we will see the reactions for preparation of ethers. Okay, the first one is your dehydration of alcohols, and the next one is your Williamson ether synthesis. Dehydration of alcohols is like this. See, this question can be asked as a mechanism question, so please understand. So first we have ROH. Okay, so here what happens, if you provide H plus, this gets protonated like this. Okay, this is your step number 1. Now step number 2, what happens, there is another alcohol if I take like this, okay, and here I have this RO plus H2 like this. What will happen, this one will attack on this one and this bond will break. So what I have now, RO plus H and R, suppose this is, I'm writing R dash, so this is like this. Now what will happen, there will be deprotonation. Okay, it is like this. What will happen, this bond will go and we will get ROR dash. Clear? So that is your preparation of ethers. Now here one thing you should remember, that this alcohol should be a primary alcohol. If you take tertiary or secondary alcohols, then you will get alkenes as the major product, not alcohols. Okay, so that is there. And in Williamson ether synthesis we have Rx plus R dash ONA. Okay, so this one will, how will this behave? This will is a nucleophile, this is an electrophile, this one will attack on this one, this bond will shift, I will get R dash OR. Okay, now this is your ether, and here what we have to remember is this Rx is a primary alkyl halide, primary alkyl halide. Clear? Okay. Now we will move to the chemical properties of ethers. So we have two reactions here. One is your cleavage of CO bond, another is the electrophilic substitution reaction. Under that we have halogenation and nitration and Friedel-Crafts reaction. You have halogenation, nitration and Friedel-Crafts reaction. Now this part is very important, cleavage of CO bond. So see, you have ROR like this, right? So when you use, let's discuss this in this one. So if you have R1OR2 and you are treating it with HX, after that this one will get protonated because it has lone pair, we will get this one, and then X minus will attack on one of them. So R1OH will form if X minus attacks here, and you will get this product. Now how to identify whether X minus will attack on R1 or R2? Okay, so basically this is a nucleophile. Okay, so what happens if R1, understand properly, if R1 and R2 both are primary or secondary, okay, then reaction will follow SN2 mechanism and X minus will attack to the less hindered side. Okay, whichever is having small group, that side the X will go. But if at all one side is tertiary or a resonated stabilized primary group is there, where if there is any resonating stabilization will happen, then X minus SN1 will follow, the reaction will follow SN1 reaction, and we will get X minus will attach to the tertiary or the resonating stabilized side. Okay, I will give example, it will be more clear. Now see here, what we have, you can see this is a primary group and this is a tertiary group. Now if a carbocation is formed here, it will be very stable. Why? Because it is having tertiary group. So in this case what will happen, SN1 mechanism will follow, this I minus will go and attack here, H will attack here, so the product formed here will be CH3OH plus CH3 whole 3 then I. Now if you see here, whenever there is phenol group, you don't have to worry, always break the bond on this side. If phenol is there, if any C6H5 ring is there, then always the product will be phenol. So you will have this one OH and CH3I. Okay. Next here if you see here, this is, I can say this is a secondary group and this is a primary group, right? So secondary, why I am saying, because see, this carbon which contains the oxygen is attached to two other carbon. This carbon which contains OH group is not attached to anything, right? So here it will be what? SN2 mechanism. SN2 mechanism, then I minus will attack on the less hindered side. This is a small molecule, this is a big molecule, I minus will attack here. So I will get like this. This one will form OH and I will get CH3I. Okay, so this is the cleavage of CO bond. Next, electrophilic substitution. So this you should be knowing, it is an electron donating group, so it is ortho and para directing. So bromination, you can take bromine and in acidic medium, so you will get here OCH3 bromine at para position and OCH3 bromine at, so this is at ortho position and this is at para position. Next, RCOCl, this is what? This is your Friedel-Crafts acylation, right? So again what we will have? We will have OCH3 and here COCl will form, and here I have OCH3 and no, not COCl, you will get COCH3, okay, and here I have COCH3. Now coming to RCl, AlCl3, so we will get here like this, we have OCH3, I will get R here, and here also it is OCH3 and I will get R here. Okay, Friedel-Crafts alkylation. This is nitration. You will get here OCH3 nitro group at ortho position, and here I will get OCH3 nitro group at para position. Okay, so these are the final reaction products. So now we are done with the reactions practice. Now we will solve some questions. Okay, so question solving, first of all I'll take the in-text questions, then some exercise questions. Good questions, 20 questions will be solving. Let us quickly see. Identify them as primary, secondary and tertiary. So here what you have to check, see, the carbon which contains the OH group, that carbon is attached to how many carbon? Carbon containing the OH group is attached to only one carbon, so this is your primary. Carbon containing the OH group is attached to one carbon, so it is also primary. Here carbon containing the OH group is attached to one carbon, primary. Here carbon containing the OH, this carbon, it is attached to two carbon, this one and this one, so it is secondary. Now carbon containing the OH group, this carbon is attached to two carbon, so it is also secondary. Next, carbon containing the OH group, this carbon is attached to three carbon, so it is tertiary. Next, identify allylic alcohols in the above example. Now what is allylic alcohol? See, if you have like this, the carbon which contains the OH group is attached to the carbon which is having a double bond. Okay, carbon containing the OH group is attached to a carbon having double bond, then it is called allylic. So if I see here there is no double bond, yes, here there is a double bond. So you see carbon containing the OH group is attached to a carbon having double bond. So yes, this is one allylic carbon. Now here no double bond, here can I say? Yes, here also you can see the carbon containing this carbon is attached to a carbon which is having a double bond. So yes, this is also allylic. Next, here you can see, can we say this carbon? Yes, you can say this carbon which contains the OH group is attached to a carbon having double bond. So yes, this is also allylic. Now at this time I also want to tell you what is vinylic. See, if you have C double bond C, okay, and the OH is directly attached to this one, then it is called vinylic. Allylic means the C double bond C is there, to the next carbon OH group is attached, that is called allylic. OH attached directly to C double bond C, that is called as vinylic. Okay, now we will go to 7.2. Name the following compounds according to the IUPAC system. We'll quickly do this one. So first of all you have to start the numbering from here. 1, 2, 3, 4 and 5. Right, so this, if you see second one, here what is attached? Here one substituent is attached. Yes, so numbering, if I do like this, now second carbon, this is what is the name of this substituent? You can see this is 1-methyl ethyl, and here I have chloromethyl, right? So basically that alphabetically this one will come first, so it is 3-chloromethyl. Okay, then I have 1-methyl ethyl, 2-methyl 2-methyl. On the second position we have a methyl ethyl group, okay, and then it is pentanol, okay. Now here I can see I have 2 OH groups, so 1, 2, 3, 4, 5, 6, right? So on first and third position I have, right? So I can write like this, and on 5 and 2 I have also methyl, so I can write 2,5-dimethyl, okay. Then I have hexane at what position? So 1 and 3, 1,3-diol, okay. Similarly here if you see 1, 2, 3, this is 3-bromo cyclohexanol, okay, simple. This one you can see a double bond, so we will start the numbering from this side, 1, 2, 3, 4, 5 and 6. So I have here hex 1En 3Ol, okay. Next here we have 1, 2, 3 and 4. So you can see bromo will come first alphabetically order, so I will write 2-bromo, then I have 3-methyl, then I have but 2En 1Ol, right? So you have but 2En 1OL. Clear? Okay, next 7.3 I missed 7.4.5. Okay, fine, we'll do this question. Give the structures of the product you would expect when each of the following is reacts with HCl, ZnCl2, HBr and SOCl2. Okay, so I will do one product. So first of all, if I have butane 1OL, so it is like this: CH3 CH2 CH2 CH2OH. Okay, now this one is reacting with HCl and ZnCl2. So you remember, this is what Lucas reagent. Lucas reagent does not react with primary alcohols, right? So here there will be no reaction. Next, if you see here, I have with HBr. So yes, with HBr what will happen? With HBr, this one will be replaced with bromine. So I'm just writing like this: CH3 CH2 CH2 CH2Br. With SOCl2 what will happen? This one will replace with Cl group. So CH3 CH2 CH2 CH2Cl. Okay, next we have here 2-methyl butane 2OL. So you have like this: 2-methyl butane 2OL. Okay, now if you see, this is an HCl ZnCl2. This is what? This is a tertiary alcohol, so this one will react, and here this OH will be converted to, so I will write like this: this one will be converted to Cl. Now if I have next one, that is your HBr. Okay, in HBr this one will be replaced with bromine, so I will get CH3 CBr CH2 CH3 and CH3. Now with SOCl2 also what will happen? This one will react with chlorine, or it will be replaced with chlorine, so I will get like this product. Okay, got it? Now 7.7, predict the major product of acid catalyzed dehydration of. So here we have to take care of Saitzef rule. So you have 1-methyl cyclohexanol. Okay, this is, I am doing 7.7, first one, 1-methyl cyclohexanol. It is like this, right? Now when dehydration takes place, what are the two possible products? So see, this is carbon, right? This is a beta carbon, and this is also beta carbon. So from beta carbon H will be removed and OH will be removed. So we can have one product like this. If I remove one H and OH from here, so I will get a product like this. Okay, this is one possibility. And if this H and OH will be removed, we will get a product like this. Okay, now according to Saitzef rule, we have to see the more substituted alkene. Check around the double bond. Here we have 2 carbons around double bond, right? Here if you see, okay, here you have 1 carbon, here we have 1 carbon, 1, 2, and to this side it is attached 1 carbon, right? So total we have 3 carbons. So obviously this is more substituted one, right? So so what will be my product here? The product for 7.71 will be the more substituted alkene, and that is this one. Okay, next butane 1OL. If you have butane 1OL, so definitely you will get but 1ene. Here 1 OL is there, H and OH will be removed, you will get an alkene here. Next, ortho and para nitrophenols are more acidic than phenol. Draw the resonating structures of the corresponding phenoxide ions. Okay, so if you see ortho and para nitrophenols, so we have like this. So I'll just do some of the structures. See, ortho, if it is there, it is like this: O minus. Okay, this is the structure of nitrogen, and we have like this. So first what will happen? This bond will shift here, this bond will shift here, and this bond will shift here. So what will be the structure I will be getting? Here I will get double bond here. This is N, this is O minus, this is double bond O here and here. Next what will happen? This one will come here, this one will come here, and this one will come here. So what I will get here? You will get here like this, this, and this, and we have this one. Okay, Next we will have this one will come here and this one will come here. So you will get a structure like this. Here double bond O, and here you will get NO2. Next this one will come here and this one will come here, and we will get this one, okay, and here I will get O minus and here I will get NO2. The same thing for phenoxide. If it is at para position, it will continue. Can try that doing. Okay, I'll do for ortho, can do for para. Next, write the reactions involved in Reimer-Tiemann reaction and Coles reaction. We have already discussed. This is your Reimer-Tiemann reaction where we get salicylic aldehyde, and this is your Coles reaction where we get salicylic acid. Okay, these two name reactions very important, so please remember it. Next, write the reactions of Williamson ether synthesis of 2-ethoxy-3-methyl-pentane starting from ethanol and 3-methyl-pentanol. Okay, so you have here, you have 2-ethoxy-3-methyl-pentane. Okay, so I have the structure first. Let me draw this structure. So it is okay, I'll draw like this, 2-ethoxy, one second, oh sorry, let me, okay, so it is CH2 CH3. So at the second position it is ethoxy, third position it is methyl, 2-ethoxy-3-methyl pentane. Okay, 2-ethoxy-3-methyl-pentane structure is like this. I have to construct this one using these two reagents. Okay, so if you remember, the Williamson ether synthesis takes place between Rx and R-ONA. Okay, and this group should always be an what I'll say, primary group, right? So I will take this group, ethyl group, as this Rx group, and this one I will take as R-ONA. So what I will get, see, if I just write down, yes, so let me take like this, CH3 CH2 CH2 O minus Na plus, okay, and I have here CH3. Okay, so it is, I think, 1 2 3 3 methyl, and the sodium ethoxide is there. Now if this one I am reacting with CH2 CH3, so what will happen, this one will attack on this carbon, this bond will go and this part will attach here, and we will get the product like this, CH3 CH2 CH CH3, then C, I have CH3 and I have O minus and CH2 CH3. Clear? We'll get this one, the product. You should be careful what should be your alkyl halide and what should be your alkoxide ions. Next, which of the following is an appropriate set of the reactants for the preparation of 1-methoxy and 4-nitrobenzene, and why? So if I want 1-methoxy 4-nitrobenzene, what is the structure here? It is like this, 1-methoxy and I have 4-nitrobenzene. So whenever a phenol group is involved, definitely this has to be your sodium alkoxide part. Okay, so this one is the alkoxide one, O minus Na plus, this one will attack on this one and you will get this one. So this is the correct choice. Okay, why you should be writing, because here the alkyl halide is primary. Okay, and here this bond cannot break, because we know that this is having a partial double bond character, so that is why this has to be the correct choice. Okay, next, predict the products of the following reaction. So this is, I think, your hydrolysis. So I told you, if one side this is primary, this is also primary, then SN2 mechanism will favor and the less hindered side will take the bromine. So what I will get here, CH3 CH2 CH2 OH plus CH3 Br. Next, here if you see, if phenol group is there, always it will break here and you will get a phenol. If benzene ring is there, there is no doubt that you will get one phenol and C2H5Br. Okay, now here also what, okay, here we have concentrated H2SO4 and concentrated HNO3. That is your sulfonation. This is what? Ortho-para directing. So sulfonate group will be, it is nitration. Nitration will take place at ortho position and at para position. I will get OCH3 nitro group at ortho position and OCH3 nitro group at para position. Next, again there is cleavage of HI. So you can see here a tertiary group is there. Tertiary group means it will follow SN1 mechanism. Carbocation will form. Carbocation will take the iodine group. So I will get the product like this, Ci plus this side it is C2H5OH. Clear? Okay. Now we will move to the in-text question. What is meant by hydroboration oxidation reaction? Explain with an example. So I told you already during the reactions, hydroboration oxidation is addition of, so just remember like this, addition of H and OH by anti-Markovnikov's rule. Okay, but exactly what happens? See, diborane reacts with alkene to give trialkyl borane as addition product. This is oxidized to alcohol by hydrogen peroxide in the presence of aqueous sodium hydroxide. So do not worry. So first of all, what happens? See, this is an alkyne, you have H and BH2. Okay, so what will happen? BH2 will attack to the, like H will attack here, that is the less I can say the negative part will attach here, the Markovnikov's rule, and here it will be BH2 attached. Okay, another time again if you do, it will continue like this and you will get a triboron alkyl derivative. Then finally you will get H and OH attached according to the anti-Markovnikov's rule. So this mechanism, please remember, very important question. Next, while separating a mixture of ortho and para nitrophenols by steam distillation, name the isomer which will be steam volatile, give reason. Steam volatile means it will be easily vaporized. Now if you see ortho and para nitrophenol, okay, so this is structure is like this. You have here NO2, this is ortho nitrophenol, and this one is para nitrophenol. Okay, so in case of orthonitrophenol, what happens? There is intramolecular hydrogen bonding. In case of paranitrophenol, what will happen? It is like this. In case of orthonitrophenol and paranitrophenol, this is intermolecular hydrogen bonding. So this intermolecular hydrogen bonding is very strong. So what will happen? It will take more time to evaporate. It will not volatile. Whereas this one, because it is not bonded to other molecules, it can easily evaporate. So can see here the ortho and para isomers can be separated by steam distillation. Orthonitrophenol is steam volatile, or I can say easily it can vaporize due to intramolecular hydrogen bonding, while the paranitrophenol is less volatile due to intermolecular hydrogen bonding, which causes the association of molecules. You can see the example here. This is intramolecular hydrogen bonding, this is intermolecular hydrogen bonding. Okay, this is important question. Next, give two reactions which shows the acidic nature of phenol. Compare the acidity of phenol with that of the ethanol. So we have seen that reaction with Na and NaOH will give you. So you can see here reactions with Na will give you the acidic nature, reaction with NaOH will also show you the acidic nature. The rest part is compare the acidity of phenols with ethanol. So definitely the phenols are more acidic. Okay, phenols are more acidic than ethanol. Why it is like this? So if you see, phenol is there like this. Okay, when it will form acid, okay, it will donate one H plus. If it donates one H plus, we will get O minus ion, right? And we have here ethanol. We'll get O minus ion here. Now if you see, this one is, this negative charge is distributed, or I can say more stabilized. Okay, so if conjugate base is more stabilized, then acidity will be higher. But here if you see, this is an electron donating group, so here O minus will be less stabilized. Okay, next question, how are the following conversions carried out? Propene to propane to OL. First one, if I see propene, right, propene to OL. So this is very simple addition of water following Markovnikov's rule. So what I have to do? H plus and water. Okay. The second one here is benzyl chloride to benzyl alcohol. You have benzyl chloride. Benzyl chloride is like this. See, sorry, benzyl chloride. Yes, benzyl chloride to benzyl alcohol. We can see this chlorine is not attached to the ring, it is attached to the chain. So this can be easily substituted using aqueous KOH, nucleophilic substitution reaction. Ethyl magnesium bromide. Okay, you have ethyl magnesium bromide to propane 1-OL. Okay, so we have here propanol. Okay, so now you see we total need 3 carbon. Already I have 2 carbon here, so I just need 1 carbon here, right? And always remember, whenever you are getting a primary alcohol, then the reactant must be a formaldehyde. Okay, so if you take this one and acidic medium, so what will happen? This is plus, this is minus, this one will attack here, this one will go here. So you will get OMg plus, then you will get OH, and you will get this as the final product. Next, methyl magnesium bromide. See, next one is your fourth one, methyl magnesium bromide, and that is reacting to give you 2-methyl propane 2-OL. 2-methyl propane 2-OL. Okay, now see, whenever I am getting a tertiary alcohol, it should react with a ketone. So I have here one acetone group like this. Okay, in H3O plus medium, what will happen? This one will react with this one. We will get this as the product here. Clear? Next, illustrate with example the limitations of Williamson ether synthesis for the preparation of certain types of ethers. So we know that in a Williamson ether synthesis we can only take primary halides. Okay, so we cannot take tertiary halides, otherwise the reaction will give you alkene as the major product. So that is the limitation C. The main limitation of Williamson ether synthesis is that it cannot be used to prepare unsymmetrical ethers where the compound has tertiary or secondary alkyl groups. For example, a reaction between a tert butyl bromide, okay, and a sodium methoxide will yield you one alkene. It will not give you a ether. So this is the major drawback. This is due to the formation of alkene and the dominance of the competing elimination reaction over SN2. That is the main demerits of this Williamson ether synthesis. Next, write the equation of the reaction for hydrogen iodide with 1-propoxypropane. So we have like this, 1-propoxypropane. So here basically you can see both the side it is same thing, so it doesn't matter anything. You can add H and I to any side. So you will get CH3, CH2, CH2OH, okay, and here you will get CH3, CH2, CH2I. Okay, next one, the first one here. Second one here is methoxybenzene. You have like this. So whenever there is a benzene group, I told you phenol is the major product here. So I will get OH here and I will get CH3I. Okay, next, third one is benzyl ethyl ether. It is like this, benzyl ethyl ether. One second. Okay, ethyl, right? It is like this. Now see, here also if a carbocation is formed here, this carbocation is very stable due to resonance. So I told you if a stable carbocation is formed, then it is SN1 mechanism. Carbocation will form here, I minus will go here. So we will get here CH2I plus CH2, CH3, CH2OH. Clear? Okay. Next, question number 19. So how do you synthesize the following alcohols from the appropriate alkenes? Okay, first one. So if you take this alkene, CH3, okay, and this one. So what will happen? Markovnikov's rule will be followed, and if I take H plus and H2O, Markovnikov's rule, OH will go to the carbon having less number of hydrogen. Here how many hydrogens are there? Here we have 2 hydrogens, right? Here we have 0 hydrogen. So OH minus will attack here and I will get this one, okay. Next, second one, if I see, I want here, so I can just tick like this. One second, okay, I'll draw that another structure. It is like this. It is like this, right? Here one CH3 group is there. So if I just take a double bond here, then again Markovnikov's rule, OH will attack on this one. Next, third one, here it is there, okay, 1, 2. So here you have to take OH here, okay, then only the Markovnikov's rule, OH will attack here. If you attack here, then it will come here also, it can come here also. We can get both the products, but we want only the major one. So this has to be the correct alcohol, alkene. Next, fourth one here. Fourth one is also very simple. I can put a double bond here. So again, here there is more substituted carbocation will form, or more stable carbocation will form. So OH minus will attack here, H will attack here, okay. Next, preparation of ethers by acid dehydration of secondary tertiary alcohols is not a suitable method. Give reason. This is also very important question. So generally when we prepare ethers by alcohols, I told you we have to take primary alcohols. Now why cannot we take secondary or tertiary alcohols? See, because it is accompanied by the formation of alkenes. The same problem, you will get alkenes as the major product and is not suitable for the preparation of ethers from acid catalyzed dehydration of secondary and tertiary alcohol, as this reaction involves SN2 mechanism, but dehydration of secondary and tertiary alcohols follow SN1 due to the steric hindrance and tend to form alkenes preferably, okay. So basically what happens, there is more tendency to form alkenes of secondary and tertiary, because here when the secondary and tertiary is there, the reaction will follow SN1 mechanism and not SN2 mechanism, okay. So that is why you can get alkenes as the major product. So this is the main thing that you should remember, okay. So there are two things that you should remember, that in Williamson ether synthesis, okay, see, I'm just summarizing in, we have this Rx plus R dash ONA. This Rx should always be primary, okay, that's the first thing. If you take this one as secondary or tertiary, then you will get alkenes, okay. Similarly, for next what we have, this one, that is preparation of ether. Preparation of ether, you have to take this ROH, dehydration of ROH. If this ROH is secondary or tertiary, then also you will get alkenes, okay, that's the first thing. And one more thing I want to write down here. So in the cleavage of ethers, right, suppose I have like this CH3, CH2, OCH3, and you have given HI. In that case, what will happen? SN2 mechanism will follow, right? Here this side there is less steric hindrance, so here I will attack. So what I will get? CH3, CH2, OH plus CH3I. Now here if you give excess of HI, okay, then what will happen? This will initially it will form, then since excess of HI will there, so what will happen? This one will also get converted like this. See, it is like this OH, and excess of HI, this will get converted to O plus H2 because of this H plus, then I minus will attack and we will get CH3, CH2I, okay. So that is the thing that you should be knowing. I think with this we have covered most important questions of alcohols, phenols and ethers. Some 5 marker mechanism based questions are there. I know that I will discuss in the 5 marker video. So these are your some important 2 or 3 marker questions that is required, okay. So that's all. Next we will see the next chapter, that is aldehydes, ketones and carboxylic acid. So let's begin. So students, now we have done with haloalkanes and haloarenes, aldehydes, alcohols, phenols and ethers. Now we will quickly revise the reactions of aldehydes, ketones and carboxylic acids. Okay. So here first we'll see preparations of aldehydes and ketones, then only aldehydes, only ketones, their chemical reactions, preparations of carboxylic acid and the reactions of carboxylic acid. Okay. So let us quickly revise this one, students. So if we have those methods where we can prepare both aldehydes and ketones, the first one is your oxidation of alcohols and dehydration of alcohols. So you have already studied these two methods. Oxidation of alcohols, if you treat it with PCC, primary alcohols, it will get converted to aldehydes, and dehydration of alcohols is copper at 573 Kelvin. Primary will give you aldehyde, secondary will give you ketones, and here hydrocarbons we will understand right now. Okay, so first two parts I am just not explaining, 1 and 2 I am leaving it. Here you can see when you have ozone with H2O, the bond will break here, oxygen will be added on both the sides. Okay, that is your ozonolysis. Next, what happens here in case of alkyne, here I will explain this one, how does it take place, understand quickly. So if I have ethyne, okay, so just a minute, yes. So if I have ethyne group, so what will happen if I have ethyne group here and I add H plus, yes, I add here H plus, okay, in presence of Hg2 plus. Then what happens here, H and what if I add like H and OH or water in presence of this one, so I will get H double bond OH. Okay, now there is a what happens now, there is a tautomerization taking place, and we will get here CH3 C double bond O and H. Clear? Okay. So next one is your preparations of only aldehydes. Okay, so we have these reactions. So one second. Okay, so preparations of only aldehydes, the first one is here from acyl chlorides. This is very important reaction, name reaction is Rosenmond reaction. From nitriles and esters, you can use Stephan reduction. So from nitriles we can use Stephan reduction or dibyl H. I will explain. Then from esters we can use only dibyl H. Then from hydrocarbons, so here we have a lot of reactions. Oxidation of methyl benzene, it involves two processes. One is your Itard reaction and another one is use of CrO3. Okay. Next you have chlorination of side chain, and then you have Gattermann-Koch reaction. Let us quickly see these reactions. So the first one, if you see, was your from acyl chlorides, right? If you take acyl chlorides H2 and palladium barium sulfate, this chlorine is replaced with the H group. That is your Rosenmond reaction, right? So from acyl chlorides, please remember Rosenmond reaction. Next, second one is your from cyanides. Okay, so if you take SnCl2 and HCl, you will get RCH double bond NH. This is a imine group formed. Okay, and after that, if you treat it with H3O plus, you will get RCHO. Okay, aldehyde. Next, here you can directly convert this RCN to RCHO by using diisobutyl aluminium hydride. Okay, next we have here and another is from esters. So using esters also directly we can convert it by using dibyl H. Okay, the third one is your what, from oxidation of methyl benzenes. So if I take any methyl benzene and I treat it with CrO2Cl2 and CS2, you get here CHOCrOCHCl2, this intermediate is formed, and then H3O plus we get RCHO, and this is your Itard reaction. You can also treat it with CrO3, okay, and you will get an intermediate like this, and then CrO3 in acetic anhydride you will get an intermediate like this, and on hydrolysis you will get again benzaldehyde. Okay, and the next one is your side chain chlorination. So you have Cl, you just treat it with chlorine and H nu, here chlorine will come, then treat it with water, OH will come, and then it will undergo dehydration to give you RCHO. After that we have here benzene COHCl and anhydrous AlCl3CuCl. So that one will give you RCHO, and you will get benzaldehyde. Okay, so these are the different reactions that you should remember. Then preparations of only ketones, we have here three methods. One is from acyl chlorides, like we had from your acyl chlorides in the preparation of only aldehydes also. Then from nitriles, there also we had from nitriles, and then from substituted benzene. This is the easiest one. This is nothing but Friedel-Crafts acylation. We all have studied this reaction. Now coming to alkyl chlorides, how can we do acyl chlorides? You have to treat it with R2CD, that is alkyl cadmium, dialkyl cadmium. This Cl group is replaced with R group. Okay, that is the first one. Second one is what? From nitriles. So with nitriles you take Grignard reagent. So you see this is plus, this is minus, this is minus, this is plus. So this one here will take C6H5 and here it will take MgBr. Now if I do hydrolysis, what will happen? Here I will get COC6H5. Okay. Next we have here chemical reactions of aldehydes and ketones. Quickly I will show you all the chemical reactions that we have. So first one is your nucleophilic addition reaction. Under that we have 5 addition reactions: addition of HCN, addition of NaHSO3, addition of Grignard reagent, addition of alcohol, and addition of last one is ammonia and its derivative. Okay, nucleophilic addition reactions of aldehydes and ketones. The second one type of reaction is the reduction reaction. Aldehydes and ketones can be reduced to alcohols, that is one type of reaction. It can be reduced to hydrocarbons, that is your second reduction reaction. The next one reaction for aldehydes and ketones is your oxidation. Aldehydes and ketones can be oxidized to the carboxylic acid or salts of carboxylic acid. So for here also we have 3 reactions. One is your Tollens reagent, Fellings reagent, and your haloform reaction. Reduction, oxidation over. Now reactions due to alpha hydrogen. So this is very easy one: aldol condensation and cross aldol condensation. Next one is your other reactions. Here we have Cannizzaro reaction and electrophilic substitution reaction. So now first let us see here addition reaction. We have this 5 addition reactions. I have already explained you. So generally if you see the mechanism, this is the carbonyl group, right? So any nucleophile comes, it will attack on this electrophilic carbon. Okay, it will attack on this electrophilic carbon and we will get Nu attack here and OH attacked here. Okay. So first of all you can see the first addition, that is what? Addition of HCN. H plus and Cn minus is there, plus will take this minus, so CCN, and O minus will take this H, OH will form, and this is called as your cyanohydrine. The second addition reaction was what? Addition of NaHSO3, right? So here what will happen? Na plus and HSO3 minus, so C plus will take OSO2H and this one will take ONA. Here there is a proton exchange, you will get OSO2Na and OH. Now here what is there? There is purification of aldehydes. This method is used for the purification of aldehydes. The third one was addition of Grignard reagent, right? This is very simple, R minus Mgx plus. So C will take the R, O will take Mgx, then with hydrolysis this O will become OH. The next one is addition of alcohols. Yes, this is important. So here we have RO minus, okay, RO minus and H plus. RO minus will attack on the carbon, okay, and O will take the H group. Now again if you attack ROH, one another molecule of alcohol, this OH will be replaced with OR dash. Okay. Now coming to the fifth one, that is your ammonia and its derivatives. So here we have H2 and this O will always be removed and you have C double bond N Z. Clear? So that is the reactions, the nucleophilic addition reactions. Next we have reduction reactions. So these are the different ammonia and its derivatives. You have to prepare this, very important. These Z groups are given, so you have to remember the name and the product formed here. This table please practice properly. Next we have reduction reaction. So under reduction there are 2 types of reduction. One is reductions to alcohols, another is reductions to hydrocarbon. Under that we have 2 reaction, Wolff-Kishner and Clemmensen reduction. Now reductions to alcohols, if you see here, we have this CO group, you can treat it with LiAlH4 or NaBH4, you will get CH2OH. Now to reduce to hydrocarbons, we have here Clemmensen reduction. You can see here OH is replaced with this CH2 group. So Clemmensen reduction reagent used is ZnHgHCl, and for Wolff-Kishner the reagent used is NH2NH2 ethylene glycol. You can use this one. Okay. Next we'll go to oxidation. So one second. Yes. For oxidation, we have Tollens test, Felling's test and haloform reaction. Tollens test and Felling's test are given by aldehydes and not by ketones, okay, and Felling's test is given only by is not given by aromatic aldehydes, okay. Now we will see here reactions. So if you have RCOH, that is your aldehyde, you just treat it with silver ammonium complex. So this will convert this one to a salt, and Ag and then ammonia and then water, okay. So this is your Tollens reagent. Next, what will happen if you take copper salt, copper ion and 5OH minus, this is the Felling solution. Here you will get RCOO minus plus copper oxide plus water, okay. Next we have here this aldehydes can be oxidized to give you acids. Now aldehydes generally, if you have this COCH3 group, whether aldehyde or ketone, this one can react with NaOX, which is your haloform reaction, and in that case what happens, this part, this RCOO minus Na plus is formed, the salt, and this CH3 part gets converted to CHX3, which is your haloform. Now if it is X is chlorine, that is chloroform, X is bromine, that is bromoform, X is iodine, that is iodoform. So generally we take iodoform, which is yellow in color, okay. So this way you can differentiate different, suppose you have been given with propanol and pentane 2-ONE, pentane 3-ONE, how will you distinguish? So propanol is having that CH3CO group, right? So that will show haloform reaction, pentane 3-ONE will not show, okay. Next we have reactions due to alpha hydrogen. So here it is what? Three conditions are there. First of all, aldol condensation should have one alpha hydrogen, okay. Next, it should be in the presence of dilute NaOH, sorry, not concentrated, in the presence of dilute NaOH, and what product is formed? Alpha beta unsaturated aldehydes or ketones are formed. Now I'll give you an example. Suppose we have taken this ethanol, okay, OH minus is there, it is a base, it will abstract this acidic proton, so we will get CH2 minus C double bond OH. Now this one will attack on another molecule of this aldehyde, so what will happen? You will get here this one, see, this one will attack here, you will get CH3, COH is present, okay, this one, and then here it is CH2, C double bond OH. Now once you heat it, okay, so this, just understand here, one second, just let me hide this one, okay. So here there is no double bond actually, okay, I was just showing it. So now what will happen, when you heat it, OH and H will be removed and we will get a double bond here, okay. Now coming to, you have this CH3COH and CH3COH, these two reactions is there. So here what will happen, so basically you don't have to do this big mechanism reactions every time to find the product. So here I have told you a trick. Suppose I want this one, right, CH3COH plus CH3COH. What you have to do, you have to just connect one alpha carbon and the other carbonyl carbon with a double bond, okay. So you have COH, CH, double bond CH and then CH3. So this product you can get within seconds just by following this trick. Next we have here cross aldol condensation. Now cross aldol condensation means what? When you have two different products, okay. Suppose you have taken acetone and ethanol. So you have, this is suppose A, this is B, so you will get four different products. One is A plus A when this one is reacting with this one, then B plus B, then you have A plus B, then you have B plus A, okay. So now what will happen, you have this acetone, so different like products I have already taken and I have given you the product. So the same trick I followed, just you have to take the alpha carbon and the carbonyl carbon, you have to connect them with the double bond. That's all you have to do for all this product and you can check this, okay. Now we'll go to electrophilic, okay, Cannizzaro reaction. So in Cannizzaro reaction, what is there? First of all, there should not be any alpha hydrogen. You should take concentrated NaOH or KOH and it is a disproportionation reaction. We get one oxidized product and one reduced product. So for example, if I have benzaldehyde and I take here the reagent concentrated NaOH, okay. So I will get this as an alcohol will form CH2OH and this one salt will form, that is COO minus and Na plus, okay. After this we have electrophilic substitution reaction. So you have here benzaldehyde electron withdrawing group, then you have Br2 and FeBr3. So here what happens, if you take like if you add bromine group, it will electron withdrawing group, it will go in the meta position, so bromine will be attached here. Similarly, if I do nitration, since nitro group will go to the and attached in the meta position, so electron withdrawing group, so it is meta directing. Okay. Now we'll come to the methods of preparations of carboxylic acid. Okay, so we have these many methods. The first one is from alcohols and aldehydes. This is very easy. You know, when alcohols and aldehydes are oxidized, primary alcohols and aldehydes are oxidized, they will be converted to acids. We just saw now the reactions of aldehydes, right? Oxidation using Tollens reagent, Fehling solution, or during haloform reaction, they all are converted to different salts of carboxylic acid. Next one is from alkyl benzenes. So here also, if you just use a strong oxidizing agent, it will get converted to benzene. From nitriles and amides. Okay, so from nitriles and amides, if we do hydrolysis, we will get benzoic acid. Grignard reagent should be reacted with carbon dioxide to give benzoic acid. Acyl halides and anhydrides. So if you have acyl halides and anhydrides, how can we convert that to acids? That I will tell you. Next we have from esters. So esters are made up of what? Carboxylic acid and alcohols. Now if you break the esters, you will get back your carboxylic acid. So half of the methods we have already studied. Let us quickly see. So the first one here is from primary alcohols. Okay, if you take primary alcohols and very strong oxidizing agent like alkaline KMnO4 or H3O plus, or Jones reagent like CrO3 and H2SO4, you will get this acid. Next we have here methyl benzenes. Okay, if you treat them with alkaline KMnO4 or KOH and heat it and H3O plus, this one will get converted to benzoic acid. Next one is your amides group. Okay, so you have RCN, H plus and OH minus will convert it into RCOH2, then which H3O plus and heating you will get your acid. Okay, so you have here RCN and with H3O plus and heating you will get RCOOH. Okay, third one. Next, fourth one is your RMGX. With carbon dioxide you will get RC double bond O MGX, and then if you heat H3O plus you will get RCOOH. Okay. Next, fifth one, with acyl chloride, if you treat it with water you will get this one. Okay, then with this one, with esters, if it will undergo hydrolysis, you will get back your acids, right? So with acyl chloride, what we can do, we can just treat it with H2O, and if we have anhydride also, we can just treat it with H2O, right? So this is your anhydride and this is ester. So this is sixth one, this is fifth one. So I wrote acyl chlorides and anhydrides, both can be treated with H3O plus or water. Okay, basically if you treat it with water, you can get your acids, and here you have to use, for esters you have to use acidified water. Okay. Next we will see the chemical reactions of carboxylic acid. Okay, so here also most of the things we have already studied. See, like we have the reactions of alcohols where we have OH bond breaking, CO bond breaking. Similarly, first reaction is cleavage of OH bond. So here generally it will react with metals and metal oxides and like Na, NaOH and NaHCO3. It is simple reactions of metals and acids. Okay, that type of reactions are there. Cleavage of CO bond, where there is cleavage of CO bond, what all reactions are covered here? Anhydride formation, esterification, we have already studied. Reactions with PCl3, PCl5, SOCl2, this is also studied. Reactions with NH3, we have also studied this one. Next we have reactions involving COOH group. There we can do reduction, okay, with the lithium aluminum hydride, it will get reduced to alcohol. Then you have decarboxylation, you can use soda lime, it will undergo decarboxylation. Reactions involving hydrocarbon part, here we have, that is something HVZ reaction is there. In case of halogenation and substitution you can do, it is also an electron withdrawing group, substitution will take place at meta position. Now let us quickly see here the first one. Yes, acidic nature. Yes, so as I told you here, first of all, more acidic than phenols, because in phenol Yes, in phenol, I have a question also on this. I will be discussing. So in phenols, the phenoxide ion which is formed is having non-equivalent resonating structures, and the negative charge comes on the oxygen and on the carbon. But in carboxylic acid, in the carboxylate ion, the negative charge comes on the oxygen, and there only comes an oxygen, and we have two equivalent structures here. So that is why these carboxylic acids are more acidic than phenol. This can be a reasoning question, so please note down this one. Then reactions with metals and alkalis. So it is very basic reaction. Acid with metal will give you salt plus H2. With NaOH it will give you salt plus water. With NaHCO3 it will give you salt plus CO2 plus H2O. Okay. Next we have here cleavage of CO bond. Okay, so cleavage of CO bond you can just see like this. So first one is your anhydride formation. So now in anhydride formation, what will happen? You have these two acids here, water will be dehydrated, and then you will get an anhydride here. Second one is your esterification. We have already seen many esterification reaction. OH and H will break, you will get your esters here. Next is your reaction with PCl5, PCl3 and SOCl2. Simply this OH will be replaced with chlorine groups. Okay, so we have done with anhydride, we have done esterification, we have done, then these reactions we have done. Next we have the reactions with ammonia. So generally what happens, if you react with this one, first a salt is formed. This is an acid, this is a base, right? So we will get a salt like this. Then you have to heat it and water will form. Then what will happen from here? H2O will come out and we will get a amide here. Okay, now similarly here, suppose we have this product, simply you have to remove this one and add NH2. Simply here you have to remove, you will get NH2. After that there is a ammonia release takes place and we get phthalimide produced here. Okay, next reactions of COH group. Okay, so if you see, okay, so first of all what happens, reductions of RCOH, it can be reduced with lithium aluminium hydride or B2H6 to give you alcohols. Okay, and then decarboxylation. So if you have any salt of carboxylic acid and you treat it with NaOH and CaO and you heat it, you will get alkanes, RH plus Na2CO3. Okay, this is clear? Okay. Now we'll do solving questions, but before that I will be explaining you the last part, the HVZ reaction. Okay, very important. So if you have, for example, CH3COOH, okay, and you use the reagent X2 red phosphorus, so what will happen? This H will be replaced with X. So what I will get here? CH2X, and we have C double bond OOH. Clear? That is the HVZ reaction. Next, if we have electrophilic substitution reaction, okay, you have this COOH group, okay, and suppose you are doing nitration, for example, you treat it with concentrated HNO3, okay, and concentrated H2SO4. Okay, so nitro group will come here and I will get COOH NO2. Okay, so that is your, so generally what I am going to say here is substitution reactions, because it is an electron withdrawing group, it will always take place at the meta position. And here the alpha hydrogen, this is very important reaction. Okay, it is definitely going to ask in the exam, so please prepare its statement properly. Clear? So these were all the reactions of carboxylic acids, aldehydes and ketones. Quick recap, and then we will start solving questions now. Okay, now let us see the questions from this chapter. So first of all, ethyl benzene, how will you convert it to benzoic acid? Simple, by treatment with KMnO4, right? So if I have this one, you have ethyl benzene, okay, and if you treat it with KMnO4, you will get acid here. Okay, next, second one, acetophenone, also you can do the same way. Okay, you can take this one and you treat it with KMnO4 and you get here COOH. Okay, next third one, what we can use, bromobenzene is there, right? Bromobenzene, yes, this is important one. Once you take bromobenzene, you just treat it with Mg and ether. Okay, you will get MgBr. Okay, after that we have this CO2 group, and this one will convert here to COOH. Okay, next fourth one is your phenylethene. Okay, so if you have like this phenyl and then is connected to ethene. Okay, so this also you can just treat it with alkaline KMnO4. Okay, or sorry, first you can do like convert it to ethyl benzene, so just treat it with H2 and nickel. Okay, convert it to ethyl benzene and then treat it with KMnO4. Okay, done. Now we will have next, how will you convert the ethanol into the following products. Okay, so ethanol, butane 1,3-diol, but2-en1l and but2-en oic acid. Okay, so first of all we will see, we have ethanol, that is CH3COH. Okay, okay, one second. Okay, so now what I can do, first I can convert it, you see the number of carbons has increased, so we will do aldol condensation, and first I will get here with alkaline NaOH. Okay, so what we'll get here, CH3, so let me just write down the product, it will give me COH, CH2, COH. Okay, now again if I reduce it, okay, so what it will happen, that is your reduction LiAlH4, or you can use NaBH4, you will get CH3, CHOH, CH2, CH2OH. Okay, so butane 1,3-diol we got. Next, but2-en1el. So if I just get this one and then I heat it, here there will be dehydration and you will get CH3, CH double bond, CH, COH. Okay, so this is your second one. Next, third is but2-en oic acid. So if this one is there, if I oxidation of this one, if you do, okay, how can you do oxidation? You can use, right, for example, KMnO4, KOH, so it will oxidize to give you CH3, CH double bond CH, COOH. Okay, clear? So that is how will happen, this all conversions can be done. Next, an organic compound with molecular formula C9H10O forms 2,4-DNP, okay, and reduces the Tollens reagent and undergoes Cannizzaro reaction. Reduces the Tollens reagent means it must be an aldehyde, and undergoes Cannizzaro reaction means it does not have an alpha hydrogen. On vigorous oxidation, it gives 1,2-benzene dicarboxylic acid. So I can just guess this product like this, it is C6, 7, 8 and 9. So if this is the product, you see everything is satisfied. 2,4-DNP it will react because it is having an aldehyde group. Because it is an aldehyde, it will also reduce the Tollens reagent, and it is an aromatic aldehyde, so it will give you Tollens reagent but not Fellings reagent. Cannizzaro reaction, yes, because there is no alpha hydrogen, and on vigorous oxidation it will undergo oxidation, both of them will get converted to 1,2-dicarboxylic acid. Okay, next, an organic compound A with molecular formula C8H16O2 was hydrolyzed with dilute sulfuric acid to give a carboxylic acid B and an alcohol C. So when you are getting B and C, one carboxylic acid and one alcohol, you can easily guess that A is an ester. Okay. Next, oxidation of C with chromic acid produced B. That means B and C will have same number of carbons. Okay. C on dehydration, which is an alcohol, gives but1-ene. Okay, so write the equations for the reactions involved. So we can have this one C8H16O2, one ester. I can have like this CH3, CH2, CH2, CH2O, CO, CH2, CH2 and CH3. Okay. Then to give a carboxylic acid B and an alcohol C. So this will break like this, okay. To give you a carboxylic acid, to give one alcohol and one carboxylic acid, okay. This is C and this is B. Next, oxidation of C with chromic acid produced B. Okay, so if this one is oxidized with chromic acid, okay, sorry, not this one, B. If B is oxidized with chromic acid, it will give you C. Okay, C on dehydration. If we dehydrate this one, okay, C on dehydration will give you butene, that is clear. Okay, so this will be the product here. So write all the reactions involved. So I have written the reactions. You have to write it in full sentence and write it clearly. Next, arrange the following compounds in the increasing of order of their property as included. Okay, reactivity towards HCN means it is a nucleophilic addition reaction, right? So we need, first of all, aldehydes will be more reactive than ketone. So I can see one aldehyde, here one ketone, here a ketone, and there also a ketone. So first, definitely this has to be more reactive. Okay, next, this is a ketone. Here you see the bulkiness is more and there the bulkiness is less. Less is the steric hindrance, more is the reactivity, right? Di-tert-butyl ketone is like this. If you see like this, the structure is like this. Di-tert-butyl ketone, and then you have methyl-tert-butyl ketone. Okay, these are the two structures here. So definitely this is less steric hindrance, so this will react. So after this one will come, okay, then we have this one, and then di-tert-butyl methyl ketone. Next you have here acidic strength. Okay, so if acidic strength is there, what will be, yeah, acidic strength, you can see here one bromine group is there, here no bromine group, here also no bromine group. So if there is an electron withdrawing group, the acidity will increase. So here you see the bromine group is very near, here the bromine group is after one carbon. So definitely, yes, so definitely this one will be first reactive, then this one, right? Now if you see here, we have CH3, CH, COOH, and CH3, CH2, CH2, COOH. So let me just draw the structure. This one is like this, CH3, CH2, CH2, COOH, and here it is CH3, CCH3, CH and COOH, 1, 2, 3, 4, 1, 2, 3, 4. Now out of these two, obviously here you can see there is more inductive effect. Okay, so this one will destabilize the conjugate base more, as compared to this one where we have less inductive effect. So this one will be like least acidic, so I can find this one as 4th and this one as 3. Okay, next benzoic acid, nitrobenzic acid, 3,4-dinitro-benzoic acid, and then you have methoxy acid. Okay, just a minute, I'll just write down here 1, 2 and 3 and 4. Okay, and here I have 1, 2, 4 and 3. Next you have benzoic acid, nitrobenzoic acid, dinitrobenzoic acid, and methoxybenzoic acid. So here we have dinitro, so this one 2 nitro groups are there, so this is 1, 4 nitro, this is 2, and benzoic acid is 3, and methoxy will be 4 because here it is a electron donating group. Okay, withdrawing group will always increase, donating group will decrease. Next we have here reaction based questions, so we should do such type of questions to quickly remember the reactions. These are very good. So what we can get here, KMnO4KOH, this is an oxidizing agent, you will get here COOH. Next SOCl2 heat, this will convert this one to COCl group. Okay. Next you have here NH2CO, NH2. So here there is a, this is what I can say semicarbazone. So here we will get C6H5, right? C double bond O, sorry, C double bond O will not be there. C double bond H2 and O will be removed. You will have NCO, NH, NH2. Okay. Next, here what is happening? Here you are having acylation, Friedel-Crafts acylation, or I can say benzoylation, C6H5COCl AlCl3. Okay. Next, here this is silver nitrate solution, so I will get this one will be like this. You will get COO minus Na plus. Then here we have NaCN and HCl, so this one will convert this one to first cyanohydrine, so I will get COOH, okay, and I will have this one, that is COH and CN. Okay. Next what we have is dilute NaOH. So this is your what I'll say aldol condensation reaction. So I can write down the product here. You can write, let me just try this one here. So I have C6H5CHO, okay, and below that I will write CH3CH2CHO. Okay, now this bond will form a bond here, so I will get benzene, C double bond C, then I have CH3 and CHO. Okay, clear? Okay, so what I will get here, the product, you have benzene, okay, next we have CH double bond CHO and CH3. Okay, next CrO3, this one will also oxidize this one, we will get COOH. Then 10th one, here we have double bond CH2 and then, okay, for converting this one here, first of all you can add H and OH following hydroboration oxidation. So first if I do BH3 in presence of H2O2OH minus, so what will happen? I will get like this CH2OH, and then here I can use PCC to convert this one to aldehyde. Okay. Next we'll see question number 10. Give a possible explanation for all of the following. Cyclohexanone forms cyanohydrin in a good yield, but 2,2,6-trimethyl cyclohexanone does not. So we know that nucleophilic addition, less is the steric hindrance, more is the reaction. So here there is more steric hindrance, that is why reaction is very slow. There are two NH2 groups in semicarbazide, but however only one is involved in the formation of semicarbazone. So if you see the semicarbazide structure, okay, let us just see here, semicarbazide structure, okay, so you can see here, this one is there, right? So we have NHCO, NH2, right? So NHCO, NH2, so if I draw this, where it is, where was the question, just a minute, yeah, so I have H2, okay, then I have NHCO, NH2. This is semicarbazide. Here they are asking that only one NH2 group is involved, whether another group is not involved. Now what happens here is the electrons present on this nitrogen is involved in resonance with this one. So it is not available for addition reaction. So that is why this reaction does not take place, or this NH2 group is not involved. Next, during the preparation of esters from a carboxylic acid and an alcohol in the presence of an acid catalyst, the water or the ester should be removed as soon as it is formed. So what happens, that water and ester will react again to give you your carboxylic acid and alcohol. It is a reversible reaction. So one of the reactants should be removed so that the reversible reaction is not possible. Okay, so how we can write this? So you can see in cyclohexanol the carbonyl carbon is not hindered, hence the nucleophilic CN can easily attack on the carbonyl carbon. However, in 2,2,6-trimethyl cyclohexanone the carbonyl carbon is sterically hindered due to the presence of methyl groups, hence the nucleophile CN- cannot attack easily on the carbonyl carbon. Next we have, out of the two NH2 groups in semicarbazide, one is a part of the amide functional group. In this the lone pair of nitrogen atom is involved in the resonance with the carbonyl group, hence this NH2 group cannot act as a nucleophile. Next you have seen the formation of esters from a carboxylic acid and alcohol in the presence of an acid catalyst is a reversible reaction. Okay, so to prevent or the backward reaction we have to remove the water. Okay, next, an organic compound contains 69.77% of carbon, 11.63% of hydrogen and rest is oxygen. The molecular mass of the compound is 86. It does not reduce Tollens reagent but forms an addition compound with sodium dihydrogen sulfide and gives a positive iodoform test. On vigorous oxidation it gives ethanoic acid and propanoic acid. Okay, then write the possible structures of the compound. So see, you can see that there is, you can first find out the molecular formula by using the empirical formula. So like it is, carbon is 69.77, okay, and we have hydrogen here is 11.63, then oxygen will be, if I add 7 plus 3 10, 6, 7, 13, 14. So let me just add here, this I will get 14, 9, 10, 11, 6, 7, 8, 81.4. Now if I just subtract from 81.4, so I will get 10 minus 4, 6, 9 minus 1, 8, then I have 9 minus 8, 1, 18.6. Okay, so what all things I will get here, I'm just trying it in rough, you can do it properly. So these are the percentage of carbon, right? So what is the number of moles? 69.77 by 12, okay, 11.63 by 1, 18.6 by 16, okay. So if you see 12 6 is 72, okay, and 12 5 is 60. So just I am doing a rough calculation, 5 point something I will get, here I will get 11.63 and here I will also get 16 point something, right? 16 ones are 16, 26. So again I will get 16 ones are 16 something. So the lowest number should be divided, right? So I will get here, if I just divide it with everything, I'll get 5, 11.6 and 1, okay. So if you just calculate and find out the empirical formula, you will get C5H10O. Please do the calculation, check, you will get C5H10O. Now what is the formula here? 12 5 is 72 and here 82, just a minute, 12 5 is 60, sorry, yeah, 60, 10 and 16. So I will get here 88. So let us see this part now. An organic compound contains 69.77% of carbon, 11.63% of hydrogen and the rest is oxygen. The molecular mass of the compound is 86. It does not reduce the Tollens reagent but forms an addition compound with sodium hydrogen sulfide. So it is not an aldehyde because it does not react with Tollens reagent, right? And gives a positive iodoform test, means it should have this, okay, one second. Okay, so it should have this CH3CO group, okay. On vigorous oxidation, it gives you ethanoic acid and propanoic acid. Write the possible structure of the compound. So first of all, I can find the empirical formula method, right? So I have carbon as 69.77%, 11.63%, and here I will get, this is 18.1%, right? I will get here 6 plus 1 7 plus 1 8, 18 point some percentage. Let me just calculate here. I'll get 81.4. So 100.00 minus 81.4 will give me 9 minus 1 8, and then this one will give me 1 8, 18.6, right? If I just calculate, yes, 18.6% I will get here. Okay, 18.6 6. Okay, now I want to convert it into number of moles. So 69.77 by 12, 11.63 by 1 and 18.6 by 16. Okay, so if I just calculate this one, I will get I think 5.81. Okay, then you have 11.63 and 1.16. So if you divide all this with 1.16, I will get 5, 10 and 1. So what is the empirical formula? C5H10O. Okay, this is empirical formula. Now what is empirical formula mass here? 12 5s are 60, 60 plus 10 70, 70 plus 16 is 86. Now what is the N factor? That is molecular formula mass by empirical formula mass. So that is your 86 divided by 86, which is equal to 1. Okay, so now we have got this one. This is your C5H10O, and we have to predict the structure on. Okay, so now doing this, I came to know that the structure molecular formula is C5H10O, right? Because N factor is 1. Again, if I multiply, I'll get C5H10O, right? So just let me write down. So what is the molecular formula? C5H10O. Now let us try to determine the structure. It does not reduce Tollens reagent but gives an addition product with sodium hydrogen bisulfide, means it reacts with both NaH. It is an aldehyde or a ketone because it is reacting with NaHSO3. Does not give Tollens reagent means it has to be a ketone group, right? That is the first thing. Next we have, it gives a positive iodoform test, means CH3CO group should be there. So I should have CH3CO group, and then the next 1, 2, 3, 4, 5 carbon should be there. Okay. Then on vigorous oxidation, it gives ethanoic acid and propanoic acid. So if you do vigorous oxidation, this part will be converted to an acid and this part will get converted to an acid, right? So you will get here ethanoic acid, okay, and propanoic acid. Propanoic acid. Okay, so this will be the product formed. Write the possible structure of the compound. So possible structure of the compound is this one. Okay, next, although phenoxide ion has more number of resonating structures than carboxylate ion, carboxylic acid is a stronger acid. So that is because of two reasons. Now carboxylic acid or the carboxylate ion has two similar resonating structures. The second reason is, in carboxylate ion the negative charge is always on the oxygen, which is a more electronegative atom, but in phenoxide ion the negative charges moves throughout the ring and it even goes to the carbon. Okay, so that is why these are the two reasons. So first thing, it has non-equivalent structures, phenoxide ion, whereas and the negative charge is at the less electronegative carbon atom, whereas in case of carboxylate ion both the resonating structures are equivalent and the negative charge is delocalized over two electronegative oxygen atoms in the carboxylate ion, whereas in phenoxide ion the negative charge is less effectively delocalized over one oxygen atom and the less electronegative carbon atom. So the carboxylate ion is more resonating stabilized than the phenoxide ion. Okay, so that is why that is more acidic. Next, you have to draw the structures of the following. So these questions I have taken from your PU question bank. So alpha methoxy propione aldehyde. So if you have like this is propione aldehyde, means propanol, and alpha group, here I have a methoxy group. Please adjust the hydrogen. This is like this. Second one, 3-hydroxy-butanol. So butanol means again 4 carbon, okay, and 3-hydroxy means OH group. Please balance the hydrogen atom. Next, third one, here is para-methyl benzaldehyde. This is very simple. You have benzaldehyde, okay, and on the para position you have a methyl group. Next, the fourth one is 4-methyl pent-3-en2-ONe. Okay, so we have like this 4-methyl, okay, pent-3-en and 2-ONe. Okay, so pent-3-en2-ONe 4-methyl. Next, question number 13, aldehydes are more reactive than ketones. So we have again two reasons for this. First one is aldehydes are less sterically hindered and they are having more electrophilicity. Okay, so how we can write down? Sterically, the presence of two relatively large substituents in ketones hinders the approach of a nucleophile. Next, electronically, aldehydes are more reactive than ketones because of two alkyl groups reduce the electrophilicity of the carbonyl carbon. Okay. Next, we have write the general reactions of the conversion of dialkyl nitrile to aldehyde by using dival H and expand dival H. So you have here nitriles are selectively reduced by diisobutyl aluminium hydride to imines followed by hydrolysis to aldehydes. Okay, so you can see the reaction here. Directly you can convert this one to aldehydes. Okay. Next, how does benzaldehyde react with acetophenone in the presence of a dilute alkali? Give equation. So benzaldehyde reacts with acetophenone in presence of dilute alkali. So it is a cross aldol product or cross I can say aldol condensation. So benzaldehyde is there and you have here, so let me just draw, you have one acetophenone, right? So this is acetophenone and here I have benzaldehyde. Okay. Now what will happen from here, when you take alkali medium, this one will form minus CH2 minus, this one will attack here and this one will attack here. So what I will get here, this one is formed like this, then CO and CH2, COH, okay, H and this one. Clear? Next we have give equation. So here a double bond will form and this one will be we can form an alpha beta unsaturated compound. Okay, so you will get CO, CH, double bond CH, CHO. Okay. Next is okay, just let me, next one, explain the conversion of ethyl cyanide to propiophenone with equation. Okay, so if you see here ethyl cyanide, right, that is CH3 CH2 C triple bond N, ethyl cyanide. If I treat this one, you have to convert it to propiophenone. Okay, if I treat this one with C6H5MgBr, that is your Grignard reagent, plus minus. Okay, here this one is minus, this one is plus, so just add it like this, you will get CH3 CH2 C and then I have C6H5 double bond N and I have MgBr. Okay, now here we have hydrolysis. Okay, this bond will break and I will get CH3 CH2 C6H5 double bond O. Okay, propiophenone we can get. Next, write the mechanism of addition of HCN to carbonyl compounds in the presence of a base. So this mechanism is there. First a nucleophile is generated, Cn minus, then Cn minus will attack on the aldehyde group, so or on the electrophile carbon, a tetrahedral intermediate is formed and after that H plus will attack and we will get this one. Okay. Next we have what is Clemmensen reduction with an example, Wolff-Kishner with an example, name the reagent used for the characterization of both aldehydes and ketones. So yes, you can see reductions of aldehydes in presence of Zn and HgCl is called as your Clemmensen reduction. Reductions in presence of NH2 and ethylene glycol is called as your Wolff-Kishner reduction, and for characterization you can use 2,4-DNP. Okay. Now reaction example, you can write down any example, like for example CH3 COCH3 and I have here zinc, amalgam and HCl, and that will give me CH3 CH2 and CH3. Next I have CH3 C double bond O CH3 and here I have NH2 NH2 and KOH ethylene glycol, it will give me CH3 CH3 CH2. Okay. Now coming to next, explain the effects of substituents on the acidity of carboxylic acid. Explain the acidic strength, and we have to find the acidic strength. Effect of, if you want to find the effect order, so we know that electron withdrawing group will increase the acidity, electron donating group will decrease the acidity. Next, B1, explain the acidic strength of formic acid, acetic acid and benzoic acid. So first of all, this one, if you see, formic acid is having less bulkiness, or it's what I can say is the carboxylate ions, the conjugate base is much more stable. So first is formic acid, then is ethanoic acid, and then is benzoic acid. Okay. Formic acid, acetic acid and benzoic acid. So if you see here, formic acid does not have any electron donating group or any alkyl group. So formic acid is definitely the highest acidic. Okay. After that, benzoic acid and acetic acid. We know that benzoic group is an electron withdrawing group. So after this we will have benzoic acid, and after that you have acetic acid. Okay. Next, chloroacetic acid, fluoroacetic acid and bromoacetic acid. So fluorine is more electron withdrawing group. So first will be fluoro, then will be chloro, and then bromo. Okay. So please, I am just explaining, you can write down the full answer. Explain the acidic strength of acetic acid, monochloroacetic acid, dichloro and trichloro. So definitely trichloro is there. So trichloro will be the most acidic because more electron withdrawing group is there. Then you have dichloro, then you have monochloro, and then you have plain acetic acid. Clear? I hope this is clear. Very simple. More electron withdrawing group, more acidity. Next, an organic compound A with C8H16O2 was hydrolyzed with dilute sulfuric acid to give a carboxylic acid B and an alcohol C. Okay, so when you are getting one carboxylic acid and an alcohol, then definitely this is must be an what I can say ester, right? Next, oxidation of the C with chromic acid produced D. Okay, oxidation of this one with this one produced C. Okay, means they are having same number of carbons, I can say B and C. The compound C on dehydration, compound C on dehydration gives you butene. Write the equations for the reactions involved. Okay, so I can first draw a ester of C8H16O2, right? So if I just draw an ester like this, okay, so what will happen? So first of all, when I treat, this bond will break here. Okay, after, if it breaks here, I will get one like this, CH3, CH2, CH2, COOH. Then I have here CH3, CH2, 1, 2, 3, 1, 2, 3, 4. Okay, so we have here an carboxylic acid B, okay, and one alcohol C. Oxidation of C with chromic acid will definitely give you B. Compound C on dehydration will give you but1-ene. So if I do dehydration, that is NeH plus if you take, or P2O5, you will get but2-ene. Okay, so you will get, this is the product formed here. Okay, so that's all students. Now we will move to the next question, next chapter, that is amines and then biomolecules. Okay, so students, now after doing all the big chapters of organic chemistry, we are at the last chapter. I won't say last chapter, but yes, amines is the one which is a very small and easy chapter. So let us quickly see what all things we are going to cover here. Preparation of amines, chemical reactions of amines, preparations of benzene diazonium chloride, and then chemical reactions of benzene diazonium chloride. Very quickly we will review all the reactions once again. Okay, so under preparations of amines, so yes, so I'll just give a small thing here. It is like 1. Okay, so first is reduction of nitro compounds, then ammonolysis of alkyl halides, reductions of nitriles, reduction of amides. Okay, 3 reductions are there: nitro compounds, amide and nitriles, then Gabriel phthalimide and Hoffman bromamide degradation. Okay, so if I see the first one, that is your reductions of nitro compounds. So I think I am starting from here, the reduction of nitro compounds. What reagents I can use here? SnHCl or FeHCl or hydrogen palladium with ethane. Okay, ethanol, that is reduction of nitro compounds. Second, we have ammonolysis, right? So if you have NH3 and RX, so it is a nucleophile, this one is electrophile, it will attack here, will form a structure like this, and then in NaOH what will happen? This H will go out, okay, so you will get one primary amine RNH2. Then if you again treat it with RX, what will happen? This H will be replaced with R. Again if you treat it RX, this H will be replaced with R. Again if you treat it with RX, this H, so you will get quaternary ammonium salt. Okay, now next third one is your reduction of nitriles. Okay, so nitriles, if you treat it with hydrogen nickel or LiAlH4 or sodium amalgam ethanol, then you will get RCH2NH2. And next one is from your reduction of amides using lithium aluminium hydride, you will get RCH2NH2. Next, fifth one is your Hofmann bromamide degradation using bromine and NaOH. This CO group will be removed and you will get RNH2. Okay, so remember here I always get confused, so you may get, so please be very clear. Nitro compounds reagents are SnHCl, FeHCl or hydrogen palladium. Okay, next for nitriles you have H2 nickel, LiAlH4 or sodium amalgam. And for amides you have lithium aluminium hydride. Next I have this Gabriel phthalimide synthesis. Okay, this is very important, question can be asked from here. So first of all you have to take a phthalimide. In carboxylic acid chapter we have seen how phthalimide is prepared, right? You have after that this KOH, if you take here NH, so here H and OH will form water and you will get N minus K plus. Then here you can treat it with RX, so this N will attack on this one KX and you will get NR, and then you will get NaOH, so you will get COO minus UNA plus, and here you will get RNH2. Primary amines can only be synthesized using this method. Now coming to the chemical reactions, so we have very easy chemical reactions, nothing much difficult. First is the basic nature, we will talk about the basic nature of amines. Then alkylation, we have already seen how does alkylation takes place. Then acylation, then carbyl amine reaction with nitric acid, reaction with aryl sulfonyl chloride, and electrophilic substitution reaction. So first of all basic nature. Okay, under this one we have nitration and sulfonation and halogenation. Okay, so now coming to basic nature, under gaseous phase the order of basicity is 3 degree, 2 degree and 1 degree, right? Because in 3 degree more alkyl groups are there, more electron donation can take place, and that is why the basicity will be higher. Next coming to in aqueous phase you have 2 degree, 1 degree, 3 degree and ammonia. Okay, and this is for your methyl group. Okay, if you have, like I can write like this, R2NH, okay, then you have RNH2 and you have R3N. Okay, so this is your methyl group where R is methyl group. Okay, next we have 2 degree, 3 degree and 1 degree and ammonia. Okay, now 2 degree is what here? This one will come if you have R group is equal to ethyl group. Okay, and aryl amines are always less basic than ammonia. Why? Because in aryl amines the lone pair of electrons of nitrogen are involved in resonance. Okay, next coming to the chemical reaction. So first was basicity, second was one was your alkylation. So you can see here, if any, this one is your alkylation. Okay, so what happens if you treat it with any RX, this H will be replaced with R. Okay, so H and R will form and you will get a amine group. Second one is your acylation. Okay, so in acylation also what will happen? Oh sorry, 1 second, I did a small mistake. Okay, so here one H is replaced with R, so already one R was there, one H is replaced with R, so we get 2 R and 1 H. Okay, next coming to acylation. So in acylation what happens? Again H is replaced with COR group. Okay, that is the second thing. Next, for acylation you can have two things. You can either take an acid chloride or an acid anhydride, or even benzyl. If you take benzyl, this R group as benzyl, then we call it benzoylation. So these all are your acylation reactions. Okay, so 1, 2, 3. So I'll write it as 2. because first one I wrote was basicity, second was alkylation, third was acylation. Then fourth one is your carbylamine reaction. You take a primary amines. If you just react it with CHCl3, KOH and heat, and then you get RNC, and this is your isocyanide, okay, and it produces a foul smell. Okay, now this is also an indicator of primary amines. Okay, next we have RNH2. With HNO2 or with nitrous acid we get alcohols, and with HNO2 you get N2 plus and Cl minus if this is a benzene ring. Okay, so means if it is an aniline, so I can write like this. If it is an aniline with nitrous acid, it will give you N2 plus and Cl minus. So this is reaction with nitrous acid. Clear? So almost we have done. Next was what? Next was, I think, so we have understood basic nature, alkylation, acylation, carbylamine, nitric acid. Then we have sulfonyl chloride and the electrophilic substitution. So sulfonyl chloride is used as a test for reagents, okay, as a test for your distinguishing between primary, secondary and tertiary amines. So if you have this type of primary amine, okay, so you get a salt here, and now this salt has an acidic hydrogen, right? So this one is soluble in alkali. Next here we have, if I react with this one, here we have there is no H here, so if it is not having any H, so it is insoluble in alkali. Okay, next here if you see there is a tertiary amine and there is no N group, no there is no H to react with this chlorine, so there will be no reaction here. That is how you can distinguish between this one and this one is your called Hinsberg reagent. Okay, Hinsberg reagent, and it is the reagent name here is benzene sulfonyl chloride. Okay, benzene sulfonyl chloride. Understood? Okay. Now we have this one, that is your electrophilic. So this was your sixth reaction, I think, sixth reaction. Next, seventh one is electrophilic substitution reaction. Now see, NH2 is a very strong electron donating group, so it will donate the electrons and ortho and para substitution will take place. Now if you just take bromine water, okay, this is highly activating group. So what happens here? Immediately all the ortho and para positions will be occupied. Okay, similarly if you take nitric acid, okay, nitric acid we get a mixture of ortho product and para product, that was obvious, but we also get a good percentage of meta product. Okay, why this happens we will discuss in the question. Next, coming to, if you take H2SO4, then what will happen? Sulfonic acid at the, when you take H2SO4, this has a H plus, this is our basic as basic medium, this is acidic medium, then we get a compound like this, and then there is some rearrangement to give you one NH3 plus here and SO3 minus here. Next, coming to this one, if you if I want only one bromo product, how can I do that? So I have to protect this NH2 group, or I have to reduce the reactivity or the activating nature of this NH2 group. So for that you have to react it with CH3CO whole 2O. Then here this becomes an acyl group is added here, acylation takes place. Now if I treat it with bromine and acetic acid, you will get only the para product, and if you treat it with nitric acid, you will get only the para product here. Next, after that I want to remove this one, I want back the NH2, you have to do hydrolysis, OH minus H plus, OH minus H plus, you will get these things back. Okay, so this is clear for the reaction, so please just quickly revise these reactions. Now we will go to the questions here. Now we will see the preparation of benzene disonium chloride. Okay, so benzene disonium chloride is a very important product. From here we can manufacture a lot of compounds. Okay, so first of all, if you take NH2 and just treat it with NaNO2 and HCl, you will get benzene disonium chloride, that is N2 plus and Cl minus. Okay, now from here what all things we can prepare? So if you see, you can just prepare whatever you want from benzene diazonium chloride. You can make it cyanobenzene, iodobenzene, fluorine benzene, you can just make it benzene, you can make it phenol, you can make it nitrobenzene as well as, okay. And then we have coupling reaction. So let us quickly see how we can do. So first of all, if I want chlorobenzene or cyanobenzene, okay, so you have Cu2Cl2 HCl, Cu2Br2 HBr, CuCN, KCN. So these all are your Sand-Meyer reaction. I'm not writing full, I'm just writing like this. So what will happen? Cl will be replaced here, here bromine will be replaced, here Cn will be replaced. Now you can use CuHCl or CuHBr. This is your Gattermann reaction. So to get benzene, chlorobenzene or bromobenzene, we have these two methods, okay. Next we have for iodobenzene, you can use the reagent Ki and that will give you iodobenzene. That is your first one here, and here second one we have. So let me just check how much we have. 1 2 3 4 5 6, okay, fine, 1 2. Next we have fluorobenzene. If I want fluorobenzene, you have to treat it with H plus BF4 minus. Now what will happen here? If you see, N2 plus will be there and X minus will go and BF4 minus will form. After that, if you heat it, then this nitro N2 group will go out. You have fluorobenzene and then you have BF3, okay. So you have ARF N2 plus BF3, that will give you fluorobenzene. So this is what? This is third one. Next we have here for getting only phenol, if you want if you just want here H, that is only benzene we want to produce, you have two ways. You can use H3PO2 water or ETOH, okay. As the fourth one, these two things we can do. If I want to convert it into phenol, then I can use water. So this is H2O will give you OH. Now if you want nitrobenzene, this is very important. From here questions have been asked repeatedly. So you can just use HBFO. The first step will be like this, okay. Then you heat it here. Here you have to use NaNO2 and copper. If you use this one, this group will be converted to NO2 group. Okay, so like that you can prepare all the products from this one benzene diazonium chloride. Now we will do questions. Okay, one more part is there, coupling reaction. So if benzene diazonium chloride is there, you treat it with phenol. So what will happen here? HCl will go and we will have this type of a coupled product, para-hydroxyazobenzene. Okay, similarly, and this para-hydroxyazobenzene is orange in color. Now similarly here we have reaction like this. HCl will go out and we will get para-aminoazobenzene, and this is yellow in color, okay. Now we have this one, some questions, in-text questions. How will you convert benzene to aniline? This is very easy, right? We can just take benzene, okay, then you can take nitrobenzene, make it nitrobenzene, okay. After that, for conversion of nitrobenzenes, we can use what? SnHCl, right, or FeHCl, and we will get here NH2, okay. And here what I can use? Concentrated HNO3, okay, and concentrated H2SO4. Clear? Now going to the second one, how will you convert benzene to NN-dimethyl aniline? You have benzene, okay, benzene, and then you want NN-dimethyl aniline. So I will try to write here, I want here NN-dimethyl aniline, okay. So first of all, I will get from benzene to I will get aniline, okay. First I can convert up to aniline, or NH2 I will get. Now after this what I will do, see, I will continue from here. See, after this you can just treat it with okay, so if you just treat it with CH3Cl, then one of the H will be replaced with CH3, so you will get NHCH3. Another time if I treat it with CH3Cl, then I will get here NCH3 and CH3, okay. Now what will happen? Here we will get, okay, now here we will get NN-dimethyl aniline, okay. So up to this, the first one, from here to here, the total one is your second one. I am writing in one, okay. Then ClCH2 whole 4 chlorine to hexane 1,6-diamine. So if you see here, you have chlorine, then I have CH2, 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 CH2 and Cl. Okay, now what will happen here? You see 1,6-diamine, here we have 4 carbon and now it is becoming 6 carbon. So these two things must be converted to carbon, and the best way of doing that is treating with KCN. So if I treat it with KCN, I will get CH2, 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 CH2 and Cn, right? 2 Cn groups are there. If I just treat it with lithium aluminium hydride, then what will happen? CH2 NH2 I will get, right? 1 2 3 4 5, and I have CH2 NH2 and this side also CH2 NH2. Okay, so 1 2 3 4 5 6, you can just arrange it, we'll get this one. Let us see the first question here. You have to arrange them in the increasing order of their basic strength. Okay, so first of all, whenever we have this aryl amine, okay, that is the least basic, okay, always. After that, you have to see here there is ammonia, no R group, so there is no induction effect, so we can have this one. Next, you can see here that you have primary amines, right? So primary amines are less basic because of only one R group, so I can write CH2NH2, okay, and this is also electron withdrawing group. Then we have here C2H5NH2. Okay, here there is no electron withdrawing group, and then here we have C2H5 whole 2 NH. Okay, so basically the order is 3 degree, 2 degree, 1 degree in the gaseous phase, right? So that is why we have this order. Next, if you see here, when you see this ethyl groups, okay, so that is for your basic medium, in the aqueous medium. So again we have this C6H5NH2, it will be the least one, obviously, right? Then we have here 2 degree, 1 degree and 3 degree. So we know the order is 3 degree, 1 degree and then for the order was ethyl group 2 degree, 3 degree and 1 degree, right? So 1 degree one will be C2H5NH2, right? Then 2 degree will be C2H5 whole 2, C2H5 whole 3N, and then we have C2H5 whole 2 NH. Okay, 2 degree, 3 degree, 1 degree and then this one. Next we have, this one is CH3NH2, CH3 whole 2 NH, CH3 whole 3 N, C6H5NH2, C6H5CH2 NH2. So now again we have this aryl amine, so it will be the least one, C6H5NH2. Next we have C6H5CH2 NH2, C6H5CH2 NH2. After this you see here it is methyl group. For methyl group, what is the order? 2 degree, 1 degree and 3 degree, right? So 3 degree will be the least one, that is CH3 whole 3N. Okay, next we have 1 degree, that is CH3NH2. Okay, and then we have 2 degree, that is CH3 whole 2 NH. Clear? Okay, now we will go to complete the following acid base reaction and name the products. So you can see here what will happen. First one, 9.5 if I write, there is a H plus will donated here, so you will have CH3, CH2, CH2, NH3 plus and Cl minus. Now second one here will also be like this, NH plus will be formed, C2H5 whole 3, N plus H and Cl minus. Now if I see 9.6, write the reactions of final alkylation product of aniline with excess of methyl iodide in the presence of sodium carbonate solution. So if you have aniline, okay, aniline, and you are treating it with methyl iodide. So first of all, what happened? H and I will remove and we will get here NCH3 and H. Again if I treat it with CH3I, HI will be removed and we will get here NCH3 and CH3. Clear? Okay, next question, write the chemical reaction of aniline with benzoyl chloride and write the name of the product obtained. So this is also very simple. This is your what? benzylation. So if I have this one NH2 and I just treat it with benzyl chloride, that is what you have C6H5COCl. So this H will be replaced with this group and you will get like this, that is NHCO C6H5. Okay, next we have here 9.8. Write the structures of different isomers corresponding to the molecular formula C3H9N. Okay, so I will to solve here this one 9.8. C3H9N. So I have like this a structure I can write. Okay, this is what? Propane 1 amine, propane 1 amine. Okay, next structure I can write like this, NH2, that is propane 2 amine. Okay, next I have here NC. So you have N-methyl ethanamine. Okay, N-methyl ethanamine, this is there. And then we have one more structure I can write like this. One second. Yes, I can write like this one, right? Can I? No, sorry. We have only 3 carbons, right? So here I can write like this, N, CH3, CH3 and CH3. So I can write here NN dimethyl methanamine. Okay. Now here you have to see, write the IUPAC name of the isomers which will liberate nitrogen gas on reaction with nitrous acid. So only primary amines will react with nitrous acid to give you nitrogen gas. So primary amines, you can see this is a primary amine and this is a primary amine. Do not get confused and think that this is a secondary amine. No, it is a primary amine. So here this one and this one will react with nitrous acid to give you nitrogen gas. Next, convert the following 3-methyl aniline into nitrotoluene. Okay, so first one, if I see 3-methyl aniline, so I have 3-methyl aniline, right? NH2 and this one methyl group. 3-methyl aniline to 3-nitrotoluene. So I have to convert this one to nitro group. So first of all, I can convert it using HNO2, or that is your nitrous acid. If I treat it with nitrous acid, what will happen? I will get here benzene disonium chloride, that is N2 plus and Cl minus, and I have CH3 group here. Now what will happen? Now you have to treat it with first HbF4. Okay, after that you can treat it with NaNO2 and I think Cu, right? If you remember the reagents properly, let's check once. What we used here was NaNO2, Cu and heating. Okay, so we will get this one. Okay, so I will be getting Na on NO2 plus Cu and heating. So this one will convert this to NO2 group and here I will have toluene. Okay, the second one here is what? Aniline into 1,3,5-tribromobenzene. Okay, again this is also very tricky question. See, first of all, aniline if I take and you just treat it with bromine water. Okay, so what will happen? All the positions will be occupied and you will get here NH2 1,3,5-tribromobenzene. This I will get. After that, what I can do? After this, I can convert it into by nitrous acid. I can convert it into benzene disonium chloride. Okay, N2 plus and Cl minus, Br and Br. Next, what we have here, I want to convert it into H, right? Just normal benzene. So for converting it into normal benzene, you can use what reagents? So if I just show you this one, you can see here, for converting it To plain benzene, you can use ETOH or H3PO2 and water, right? So I will use H3PO2 and water, okay? So I want to use here H3PO2 and water. So that one will convert this one to H and I will get bromine, bromine and bromine, okay? Next we'll go to account for the following. pKb of aniline is more than that of methylamine. So many reasoning questions I have taken here. So as you all know, aniline has a lone pair which is involved in resonance. It is not available for donation. If it is not available for donation, it is less basic. Less basic means higher pKb value, okay? So you can see aniline undergoes resonance and as a result, the electrons on the nitrogen atom are delocalized over the benzene ring. Therefore, the electrons on the nitrogen are less available to donate. On the other hand, in the case of methylamines, due to the plus I effect, the electron density on the nitrogen atom is increased. As a result, aniline is less basic and has higher pKb value. This is very important question. Next, ethylamine is soluble in water whereas aniline is not. So smaller the amines or the hydrophobic part, greater is the solubility, right? So ethylamine when added to water forms intermolecular hydrogen bonds with water, hence it is soluble. But aniline cannot form, cannot form hydrogen bond with water, to a very small extent, okay, can form hydrogen bond with water to a very small extent due to the presence of large hydrophobic group, okay. The ring of the aniline is a very big group and it prevents the hydrogen bonding with water, so that is why it is insoluble. Next, methylamine in water reacts with ferric chloride to precipitate hydrated ferric oxide. This is important question, okay, so please understand this one, please practice this question, it can be asked, okay. Now methylamine when it is taken in water, how does it behave? See, methylamine with water will take this H plus and you get OH minus, free OH minus, okay. So methylamine in water reacts with ferric chloride to precipitate hydrated ferric oxide. Now in the ferric chloride what we have, Fe3 plus and 3Cl minus. Now this OH minus which is produced due to this methylamine, it OH minus reacts with this Fe3 plus to give you the hydrated ferric oxide, okay. So basically methylamine is not directly related, but methylamine when it is present inside the water, it takes the H plus and it gives so many OH minus. Now when ferric chloride is there in the solution, it will dissociate to give you Fe2 plus and Cl minus. Now the OH minus that has been produced due to this methyl chloride, that reacts with Fe2 plus to give you hydrated ferric oxide, okay. Next, although amino group is ortho and para directing in the aromatic substitution, aniline on nitration gives a substantial amount of meta-nitroaniline. This I have showed you during the reaction and I told you I will explain it during the question. So see, when you take nitric acid, concentrated sulfuric acid, concentrated nitric acid, so the H plus present in the medium reacts with the aniline NH2, okay, and it becomes NH3 plus. So you can see here NH2 is there, this H plus is there from the nitric acid, sulfuric acid, so much acidic medium, you get NH3 plus. Now this NH3 plus is an electron withdrawing group and it directs the incoming nitro group to the meta position. So you can see nitration is carried out in an acidic medium. In an acidic medium, aniline is protonated to give you anilium ion, which is meta directing. For this reason, aniline on nitration gives a substantial amount of meta nitroaniline, okay. Next we have aniline does not undergo Friedel-Crafts reaction. So now if you see aniline, aniline does not undergo Friedel-Crafts reaction. Here also what happens, the NH2 group reacts with AlCl3 to form a salt like this, okay. Now this is an electron withdrawing group and it deactivates the ring, and then that is where the reaction is not possible. Friedel-Crafts reaction is carried out in the presence of AlCl3. AlCl3 is a Lewis acid while aniline is a strong base. Thus aniline reacts with ACl3 to form a salt, okay. This salt is formed here. Due to the positive charge on the nitrogen atom, electrophilic substitution in the benzene ring is deactivated. It You are understanding what is happening? This is plus charge, right? Now it is deactivating the ring. If it is deactivating, then the ring is becoming electron deficient. If it is electron deficient, it won't react with another electrophile. So that is what is happening, does not undergo Friedel-Crafts reaction. Okay. Next we will see diazonium salts of aromatic amines are more stable than those of the aliphatic amines. Yes, this is also important question. The resonating structures for the stability of the diazonium salts. Okay, so when you have diazonium salt, there is a proper resonance happening there. That is why these structures are very stable. Whereas in case of aliphatic, so when you get in this one, this N2 gas is escaped out and we get ROH as the final product, right? So because this Rn2 plus is not stable, because it is not stabilized by resonance. Here you can see it is stabilized by resonance. Okay, it is stabilized by resonance. This ring resonating happens. That is why the ring is very stable. Next we have arranged the following in the decreasing order of their pKb value. Decreasing order of pKb value means, again you have to think in terms of decreasing order of pKb value, means highest pKb to lowest pKb, right? This is decreasing order. Highest pKb means lowest base, right? Lowest base to strongest base. Okay, so that is what we have to find out. So now, as I always tell you, if there is an aryl amine, it will be the lowest one. So I can write first one will be C6H5NH2. Next what I have here, I can find that we have a secondary group and we have tertiary, primary group, secondary, and then I have this group, right? So again C6H5 group is there, means it will reduce the basicity. So I have this one C6H5NHCH3. Okay. Next after this is C2H5 and this is C2H5. So here it is primary, here it is secondary. So definitely this one will be more basic. So we have here C2H5NH2 and C2H5 whole 2 NH. So always remember the order in the gaseous phase is 3 degree, 2 degree, 1 degree, right? So obviously 1 degree will be less than 2 degree, that is there. And whenever we have aryl amine, it is always less than aliphatic amines. Okay. Next if I see here, again I can find a C6H5 and I think increasing order of basic strength. Okay. Okay, one second. Here it is asking decreasing order, so the sign will change. Okay, so this one is the least basic, it will have the highest pKb value. Similarly here I will get. Next I have C6H5, increasing order of basic strength, it is C6H5NH2. Okay. Next we have C6H5NCH3 whole 2. Then again, so again this one is a ring, so it will also have C6H5NCH3 whole 2. Okay. Next here I can have a 2 degree and here I can have a 1, like this is also CH3NH2 and this is C2H5NH. So ethyl group definitely will be more basic. So I will have next CH3NH2 and I will have C2H5 whole 2 NH. Okay. Last one, you can see third one. So you have aniline, paranitroalanine and paratoluidine. So toluidine is a CH3 group, it will donate electrons, it will increase the electron density. So basically paratoluidine is the highest one. Okay. Then we have before that aniline, no, paranitroaniline. We have paranitroaniline. Okay. Next we have aniline here. Okay, paranitroaniline, then aniline, and then we have paratoluidine. Okay, next in the decreasing order of basic strength in gas phase. Okay, so gas phase is there. So we know in gas phase what will happen, 3 degree will be highest one, then this one. So for this one, fourth one I can write like this, gaseous phase, right? So first one will be ammonia. Next we have 1 degree, C2H5NH2. Okay. Next we have 2 degree, C2H5 whole 2 NH. and then we have 3 degree, that is C2H5 whole 3n. Okay, now fifth one I have is, you have basic order. So generally alcohols are more basic, so basically you have C2H5OH more basic first. Okay, alcohols are more basic. We will also see a question why alcohols are more basic. Now again here we have 2 degree and 1 degree, so obviously we have 1 degree C2H5NH2, and then we have 2 degree C2H5 whole 2NH. Okay, next sixth one we have C6H5 C2H5. so if you see here, it is C6H5NH2, again it is the least one, right? Always the aryl amines will be the least one. Again 1 degree, then 2 degree, so I have 1 degree C2H5NH2, and I have C2H5 whole 2NH. Okay, clear? Fine. Next, give the structures of A, B and C. So we see the first question. First, CH3 CH2I with NaCN. So what it will give you? It will give you CH3 CH2 CN. Okay. Next, B, if you see, partial hydrolysis will convert this to amide. So what I will get here? CH3 CH2 CO NH2. Okay. Next, C1 NaOH and Br2 will remove this CO group, and we have CH3 CH2 NH2. Okay. Next, second one here is C6H5N2 plus Cl minus and CuCN. So that will give you C6H5 CN. Okay. Next, B, if you just treat it with H2O and H plus, okay, the hydrolysis you do, you will get here C6H5 CH2 NH2. Okay. Next, C1, if you treat it with, oh sorry, one second, here I did a mistake, hydrolysis, right? It will convert it to acid. Then if you do ammonia, again we will get a amide. So C6H5 CH2 C double bond O NH2. Okay. Next, third one here is, we have CH3 CH2 Br with KCN. It will give you CH3 CH2 CN. Okay. Then B, lithium aluminum hydride, will reduce this to CH3 CH2 CH2 NH2. Next, C1 with nitrous acid, this one will get converted to alcohol. You will have CH3 CH2 CH2 OH. Okay, clear? Okay, now I'll go to this one, Fe and HCl. So fourth one, if I treat it with C6H5NO2 FeHCl, so it will give me C6H5NH2. Okay. After that, if I treat it with NaNO2 and HCl, so here it will give me benzene disonium chloride, because it is an aniline, right? Then we have H2O and H plus. So H2O and H plus, if you remember, it converts this one to alcohol, right? Or I can get this one as phenol. Okay. Next we have fifth one here. This one will also give me benzamide. So CH3CONH2, this one will give me benzamide. Then we have A here. Then with NaOBr there is Hofmann degradation. So I will get here CH3NH2. Okay. And then with NaNO2 and HCl we have CH3OH. Okay. Next, sixth one here is C6H5NO2 and FeHCl. So it is C6H5NH2. Okay. After that we have HNO2. If you treat it with this one, it will give you N2 plus and Cl minus. So we will get N2 plus and Cl minus. And then if you just treat it with C6H5OH, this is again a coupling reaction. So we will get here like this, N double bond N, and we have OH group. Okay, clear? Okay, now we have a question. An aromatic compound A on treatment with aqueous ammonia on heating forms compound B, okay, which on heating with Br2 and KOH forms compound C of molecular formula C6H7N. Write the structure and IUPAC names of compound A, B and C. So C6H7N is nothing but is your aniline. Okay, now this was prepared, this is your C. Now it was prepared on reacting with Br2KOH, right? That means you should have an amide group here. So that is your benzamide. This is your benzamide. Okay. Next, after that, this one is treated with what? On treatment with aqueous ammonia. So if you treat it with aqueous ammonia, then this must be a benzoic acid. Okay, so this one will treat NH2 here and then you will get this one, right? So this is A and this is B. So A is your benzoic acid, okay. B is benzamide, okay, and C is aniline. Clear? Okay. Now we'll go to question number 13. Give plausible explanation for each of the following. Why are amines less acidic than alcohols of comparable molecular mass? I told you we'll discuss this question. So now see, when alcohols will donate H plus, what will form? RO minus. When amines will donate, we will get RNH minus. Now this negative charge is obviously more stable on alcohol because here the negative charge is carried by a more electronegative atom, that is oxygen, whereas in NH minus it is carried by N, which is a less electronegative atom. So as a result, what happens? This one is more stable, so it is a stronger acid. You can write it in this form. Next, why do primary amines have higher boiling point? Because they can form more hydrogen, or intermolecular hydrogen bonding is more in case of primary amines. Why are aliphatic amines stronger bases than aromatic amines? So we have already discussed. In case of aromatic amines, due to the minus R effect, the lone pair of the nitrogen is involved in resonance of the benzene ring. It is not available for donation, so its basicity is less. Okay. Next, how do you convert acetanide to paranitroaniline? So this is your acetalide, and once you treat it with concentrated HNO3 and H2SO4, you will get nitrobenzene, paranitrobenzene. Then to get back your NH2, you can treat it with OH minus and H2O. Okay. Next, explain carbylamine reaction. This is very simple reaction. So what happens? Aliphatic or aromatic primary amines on heating with chloroform and ethanolic potassium hydroxide forms isocyanide, or we can call them as carbylamine, which is a foul smelling substance. It is used as a test for primary amines. Okay, so RNH2 plus CHCl3 plus KOH gives RNC plus KCl plus water. Next, explain, okay, just a minute, this question is repeated. Yes, explain Hofmann bromamide degradation with an example. So amides on heating with Br2 or aqueous NaOH gives primary amines, and this reaction is called as Hofmann bromamide degradation. You can take any reaction like this: CH3, CH2, CONH2, and you treat it with bromine and aqueous NaOH. Okay, so this one will replace this CO group and I will get here CH3, CH2, NH2. Okay. Next, we have the pKb values of ammonia, methanamine and benzenamine are given. Okay, pKb values are given respectively. Arrange them in the increasing order of their basic strength. Okay, so if you see, ammonia value is 4.75, this is 3.38 and this is 9.38. okay, so if the pKb value is highest, then it is least basic, right? Then I can say that benzenamine is the least one. Okay, because it is having highest pKb value, so least acidic. Then we have ammonia, okay, ammonia, and then we have methanamine. This is very simple. Based on your pKb values, you can easily find this. Next, why aromatic amines cannot be prepared by Gabriel phthalimide synthesis. Okay, so what happens in Gabriel phthalimide synthesis is used for the preparation of aliphatic primary amines. It involves the nucleophilic substitution SN2, that is of alkyl halides, by the anion formed by phthalimide. So you can see here, this the anion formed by phthalimide, it attacks on this Rx, that step is there. But if you have aromatic halides, this bond cannot break here, right? But aryl halides do not undergo nucleophilic substitution reaction with the anion formed by the phthalimide. This reaction cannot take place. This bond is very strong, so that is why they do not form, or aromatic amines cannot be prepared by Gabriel phthalimide synthesis. Next, next, what is Gabriel phthalimide synthesis? This question you can now relate well. So you can see here, this is there, KOH, N plus K minus, here Rx is formed. So this one attacks on this one and this X goes out. So we find here NR group, right? But here if aromatic halo, so for example, if chlorobenzene is there, okay, now this one will attack here and Cl will go out. That cannot happen because this bond is very strong due to partial double bond character. Okay, so here we have this one N-alkyl phthalimide, then this one is getting converted here and we'll get this one. Okay, so okay, so that's all students. So I have not taken biomolecules chapter in this particular session because I have another session where I'll be discussing the most of the important questions. So there I will cover biomolecules. This video will become very long otherwise. You can just revise all the reactions that I have discussed here, and then you can do these questions, prepare the reactions and get ready for the 5-marker section video. Okay, all the very best, and if you have any doubt anywhere, please comment down. I'll definitely address to it. Okay, thank you students.